Okay, great. So we are going to start. First of all, sorry for the delay, of the past. So let us start. We have our first speaker today. It's gonna be a 40-minute talk.
No, I hope we're not gonna be
Okay.
40 minutes.
Okay, great. I will let you know when you have 5 minutes left.
Okay, yeah. So I'm aiming to talk for 30 minutes so that there's
Okay.
time for questions.
Okay, great.
And also maybe we make up some of our lost time.
Okay, great. So
yeah, let me know when it's 25 minutes in.
25. Okay, great.
Yeah, okay, great.
Yep.
Okay, yes, so I hope everyone can hear me okay, both in person and online. So I'm Betsey Adams. I'm a staff scientist at Astron, which is the Netherlands Institute for Radio Astronomy. If you've not heard of that, because you're not a radio astronomer, maybe you've heard of the NOVA Optical Infrared Instrumentation Group, who are housed in the same location. So for example, WEAVE was also built where I work. I am also one of the current co-chair of the SKA H1 Science Working Group. And so sort of in that context, I want to talk to you about H1 Science, the surveys happening with the pathfinders, and the synergies I see with JPass and J+. I am going to try to keep this somewhat short. I have a lot of potential information to share, but I hope that interesting. And I should say that my target audience that I'm talking to are the people working with JPass and J+, the optical people. There are some other H1 astronomers here. There's a good group in Granada. They don't need this information. They know it already. So this is hopefully aimed at people who are not so familiar with it. I think we're having this meeting because we all recognize that there are more than stars to a galaxy. So this is the image I have on the front of my slide, and you might wonder, why do I have this? It's not what I care about. I'm an H1 astronomer, and I care about dwarf galaxies, not massive spirals like our own Milky Way. Well, it's because if you look at this image in neutral hydrogen instead, there's this nice little dwarf galaxy up here, and you see that there's a whole lot more happening than you see in the optical when you look at the gas. And so that's, of course, why we're here. And so I wanted to sort of start with my little pitch for why neutral hydrogen is great, which I give to non-H1 audiences. So when we detect neutral hydrogen, it's a spectral line that we detect. And so the most basic way, if you think of looking at it with a single dish or unresolved data, which we'll start with, is you have a spectrum. And so you always have a spectrum. So you have your detection in that, and you have an amount of emission, which is directly your mass if you know the distance, because we understand the physics of hydrogen extremely well. And so as long as the emission is optically thin, we can directly calculate the mass. Now there's also the location of that line, which of course is your velocity or your distance if it's far enough away. And so we get this for free, or it's naturally part of our observations. There's also the width of the line. And so that width is a proxy for the rotation or your total dynamical mass of your galaxy. So all very interesting things, and you can do this all with a single dish. Now the era we're moving to, though, is even better with the SKA precursors and pathfinders, because we're going to have resolved data. So when you use an interferometer, now instead of just the spectrum, you have spatially resolved information, which means instead of just the mass, you have your distribution of H1. Instead of just the width, you have resolved kinematics. We often look at these things we call position velocity slices that we take through the cube. And what that means is you can model your rotation of your galaxy and derive a rotation curve. So you have a lot more information. And so I was really trying to think about what I would, when we come to talking about synergies, what I think the strengths of neutral hydrogen are. And so these aren't in any particular order other than the order I wrote them on the slide. So interactions and disturbances, and we saw a little bit about this. We talked about environment already in this meeting, that the H1 disk generally extends further than the stellar disk. It's sort of at the edges of the galaxy, and so it's really often disturbed first, or at a level where we can detect it more easily than the optical. So this is the same view of the same data I showed you before, just slightly different view. And I should point out that this is data from MeerKAT, part of the MIDI survey, where you have your optical galaxy here and your H1 contours on top. And what you see is we saw that extension well beyond the optical galaxy. And oftentimes you'll end up seeing these extensions or this disturbed material if you go to very low surface brightnesses in the optical to find the very faint stellar. But it's often much easier to see in the neutral hydrogen first. Now you also have your kinematics. Here we have our nice resolved velocity field of this galaxy lower down. So again, this fact that we get the kinematics for free instantaneously. And I think the other thing to point out is that we often have the spectral resolutions that we get sort of naturally in the radio, or for neutral hydrogen at least, are quite good. So we normally are easily do 5 to 10 kilometers a second resolution. So we resolve really well kinematically galaxies. The other thing that I think neutral hydrogen is excellent at, and this is what I really care about for my personal science, is low surface brightness dwarf galaxies. So things that are sort of often easy to overlook in the optical. If they're gas rich, you can find them very easily in the neutral hydrogen. And so this galaxy here, this big galaxy, of course, we knew about, but you know, this survey that was done, we picked up the little one just north of it and another one to the northwest. Where they maybe had been seen before, or if you looked at the optical data, they were clearly there, but maybe they hadn't been cataloged before, and definitely they didn't have redshifts before the neutral hydrogen. They're the sorts of things that are so faint that they're always overlooked by spectroscopic surveys. So those are the strengths, and I love neutral hydrogen, but I think if we're going to talk about synergies, we should also maybe be a little bit realistic about what I'm going to call the complications of neutral hydrogen that you might not be aware of. So I think something that I was thinking about is neutral hydrogen, the transition is actually very intrinsically faint. So we can detect it because there is lots of hydrogen in the universe. It's the most common element, but it's very intrinsically faint. And what this means, and I'll show some examples later, is that we actually have a relatively limited redshift range for direct detection of neutral hydrogen in emission. So when we talk about the SKA, we're going to be really happy that if we detect things that are the mass of our own Milky Way, and it's probably going to be a bit more massive than that at a redshift of 1, right? And so for H1, that's huge if we're going to directly detect something at redshift 1. But for, optical, maybe that's more common for you guys. You're like, oh, redshift 1, who cares? That's nothing, right? So there are techniques and approaches we use to probe to higher redshifts. So stacking, so not a direct detection, but taking thousands of spectra when you have a known optical redshift and stacking to get bulk properties of a group of galaxies, or looking for absorption against radio continuum sources where you can go to quite high redshift, but you have limited lines of sight. Now, the other big complication that I think is really important to realize, and this will come back when I talk about things again, is radio frequency interference, RFI, which is the bane of radio astronomers' existence. But the way that this manifests for an H1 survey, because it's limited in different frequency bands, it's lost redshift ranges because it is a spectral line. So there are redshift ranges where, given our current radio frequency environment, it's just not clear that we're going to be able to detect anything. And so this spec is an example where this shows from the alfalfa survey the weight. So 1 up here means like we had full sensitivity at that frequency. And then you see there are dips where we have very low sensitivity. And so the second is a big one. That is the FAA radar at the San Juan Airport in Puerto Rico. So that's what lets you get to and from the island safely, but it also means we don't observe any galaxies there. But I liked this example because you see there are 2 different colors, and these are actually from 2 different sets of observing, basically. And it shows that this interference is not always constant in time, it can change. So there can be a band that is mostly inaccessible, but sometimes is accessible. So the radar actually operates at 2 frequencies, but sometimes it only uses 1 of them. So then you access a little bit. Okay. So I also wanted to, I think maybe to try to set some common language, set some common numbers and definitions that maybe people will find helpful. These are things that float around my head a lot that I wanted to share. Okay. So the neutral hydrogen transition is 1420.40575. I lose the significant digits from memory megahertz. That's 1.4 gigahertz. So when we're talking about neutral hydrogen in emission direct detection, we're talking around a gigahertz is what I'll normally round it to. So that's the frequency range we're talking about. You go a lot lower than that in frequency. There are still things you can do with neutral hydrogen. You're going to higher redshift, but you're going to start moving away from direct detection. So when we think about an H1 galaxy, I don't think in magnitudes, I don't think in surface brightness and magnitudes per square arc second, I think in H1 mass, and I do think in a surface brightness unit, which is atoms per square centimeter. And a really useful number for that is 1.25 times 10 to the 20. So that's 1 solar mass per parsec squared. That is what I would call sort of the canonical main H1 disk. So below that column density threshold, you love it if you can probe below that. That's where you're more likely to see sort of the first evidences of interaction when they're still quite weak, if you're at a few times 10 to the 19. You go much higher than that in column density, and you're getting into maybe more star-forming gas. You generally don't get much higher than sort of 10 to the 21, because above that, then you're sort of basically converting into molecular gas generally. Okay. So there are too many, well, I find that radio astronomers, we tend to use a word to mean multiple things, or there's multiple versions of it. So a galaxy will have a typical intrinsic line width, and that's sort of how wide the width of the gas is due to sort of internal kinematic motion. So that's the temperature of the gas. So for a warm neutral medium, which is mostly what we detect, that's going to be on the order of 16 to 20 kilometers a second. That's important if you're sort of calculating a surface brightness sensitivity of your galaxy. That's the number that matters. There's also your total line width, which is if you're looking in the point source or unresolved regime, total projected line width. So that's a bigger number. And this is sort of important because these two different line widths are, like I said, they're a bit different for resolved versus unresolved sources, and how you calculate your detection limits is a bit different. I think that's going to be similar in optical, where you have a point source, you know, what sort of star you can detect, and then you have a surface brightness limit also in your images. And an important thing is that this matters for a point source if we have our integrated line flux, so the equivalent of total of apparent magnitude in a sense. And then you have the width of the line. What you see is your detection limits depend on that line width. This, you know, makes sense if you think about it. If you take the same total amount of flux and spread it out over more channels, over more velocity width, it gets more difficult to detect. But these are just some sort of things that I think are useful to know or have a brief introduction to. And I hope that you find this maybe a bit helpful and not just confusing. Okay. So I wanted to briefly talk about, before diving into some surveys that have happened or happening now, what we're sort of looking towards with the SKA as setting the stage, knowing that this is sort of the ambitions, and everything we're doing now is trying to get us there in some sense, but failing in others, otherwise we wouldn't need the SKA, right? I also want to emphasize, again, no time for the SKA has been allocated. These are just sort of schematic surveys that the community put together in order to write science cases, saying, here's the sorts of things we'd like to do. Whether they will happen in this way, where they will be pointed, none of that is decided. That will happen in the coming years. I think this also illustrates that there's a lot of different types of H1 surveys. I'm not going to talk about most of them. There's absorption work. They're studying our own galaxy. As I mentioned those the other days, you can do surveys that target individual objects where you want to do really deep observations to understand what's happening. And then there's a type of surveys I think are most relevant for the synergies we're talking about here, which is different tiers of untargeted surveys where you pick fields of sky and go deeply. And what I really wanted to point out here is the resolutions that we're talking about, because these are very different between radio and optical. So we're talking about sort of a maximum resolution of 2 arc seconds. For the deepest tier, where we would have sort of the most sensitivity. And you'll see these often scale, because as you have more sensitivity, you can afford to go to higher angular resolution and maintain sort of the same surface brightness sensitivity, or surface brightness sensitivity that's meaningful. To 10 arc second resolution. And I also want to talk about the redshift limits. Again, I think these are quite different between direct H1 detection and optical. So maximum redshift detection, we're talking around 1, but the median, even for the deepest tiers, maybe 0.5, which, I mean, from my perspective is amazing if we had lots of H1 detections at a redshift of 0.5. Our furthest right now There's some at 0.25, there's one at 0.36 maybe, you know, but that's it, right? Like it's handfuls, you can name all of them. Okay, and this is just a schematic showing you this in a different way. So rather than a table of numbers, a picture where you have redshift and your H1 mass and sort of showing like what we might detect with the different tiers predictions. And again, just showing that there's not a whole lot out at high redshift, high for H1 astronomers. Okay. So how am I going for time? Any idea? Well,
That was 15 minutes. So.
Okay, yeah, I think that's okay. So I wanted to talk about some surveys. There are so many surveys happening. I picked just 3 to go a little in depth on, and then very brief overview of some others. And I'm not, here's my motivation for why I picked these, but I'm just gonna go into talking about them. So alfalfa is the first. So alfalfa was a single dish survey. It used the Arecibo radio telescope. And it's 0 to 36 degrees of declination. That is the sky you can see from Arecibo. Picking the extragalactic sky, so you see the right ascensions here. So this doesn't have maybe the best overlap, but 30 to 36 degrees I think is some reasonable overlap with JPass and J+. It's very local, redshift less than, pretty sure it's 0.06, it's 18,000 kilometers a second, right? It's so local, I think only in velocity. I don't know what this redshift thing is. And so part of the reason I love this survey, besides the fact that I did my PhD with it, is it's done. It's fully public. There's source catalogs. You have your H1 masses. There's cross matches to Sloan and such. So it's all there ready for you to use. Now it's only global information. So it's the total gas content, the total line width, the sky overlap. It's there. So if you want to sort of understand what can I learn from neutral hydrogen and combine it, I would say this is the place to start. The catalogs are there. Go for it. Okay. The next survey I'm going to talk about, and I'm really grateful that Javier also did a super quick rundown of lots of surveys yesterday. I'm talking about some of the same and some orthogonal, is Westerbork Aperitif. And this one I'm talking about for a couple of reasons, and I'm trying to go in the order of, I think, data availability and relevance. So one is this is a survey I spent a lot of my life on. I'm still spending a lot of my life on, so it's hard for me to not talk about it. But it's also Northern Hemisphere using the Westerbork Synthesis Radio Telescope. And we did wide field surveys with it over 2.5 years because we put a new instrument or system on it called Aperitif, which is a phased array feed, which gave us, here's our large field of view image with the moon for scale, right? Okay. And surveys took place over this 2.5-year period, about 2,300 square degrees. And so this figure here, all the colored circles are where we have coverage in the end, and the color sort of corresponds to the depth. And so part of the reason I think this survey is great for this meeting is, this isn't maybe the best view, but this line here is 30 degrees declination. We stayed north of 30 degrees declination. We talked a little bit yesterday about how when you point telescopes near the equator, like MeerKAT or ASCAP, their beam starts to get elongated. This is way worse for Westerbork because it's a 1D array, so it's east-west. So once we hit 30 degrees declination, our beam is about 15 by 30 arc seconds. If we go further south below 30 degrees, we just get larger and larger. And if we stay north around, 60 degrees or something, then our beam is about a circular 15 arc seconds. Okay. So interferometers, and they have large bandwidths because we have much better computers than we did, previous generations of surveys. What this means is they're simultaneous H1 and continuum surveys. When you have 300 megahertz of bandwidth, 300 megahertz gets you decent continuum sensitivity, it turns out. You didn't bother with this with alfalfa because it was a single dish and your continuum was all confused. But with the interferometers, you can do it. Caveats here is we actually only process, depending on our frequency settings, 150 to 225 megahertz, because the rest of it is full of RFI. This is our life. And so in fact, nominally, we should have been able to have frequency settings that would take us out to a redshift of 0.25. The reality is we only take data and produce cubes and data out to a redshift of 0.1 for neutral hydrogen, because RFI beyond that. Okay. And we sort of resolve depending again on the declination we're at, changes our beam, changes our column density sensitivity, but we're sort of resolving just above the main H1 disk, or have sensitivity to just above the main H1 disk. So there is some fully public data for Aperitif. We had a first data release a while ago now. It was our first year of observations, and it was the products that come straight out of our pipeline. So this is continuum images for each beam, and our cubes, our line cubes, which are uncleaned, because there's no source finding done on those. That happens later. They're not primary beam corrected or mosaicked. So in some sense, this might be what comes sort of maybe equivalent to probably lower, slightly lower, probably what will come out of the SDP, straight out of the SKA before it goes to an SRC, and people do further things with it. So it gives you a sense of what might come from the SKA directly, but it's not the best for doing science with directly. We have been working hard to try to get to more science data products. What's available is a continuum source catalog for that first data release. We're also working on improved processing, and so we have the Butes field, which has a nice mosaic image and source catalog. And we're working on releasing all the data and applying the approved continuum processing, and have a few more fields that are coming up for that. So something you'll notice here is the continuum data products tend to come before the H1 data products. I think this is true for most H1 surveys that are doing both. The continuum is basically, well, you have to do it first. It is basically you have to produce continuum images on the way to making your H1 data cubes. And also it's easier in terms of data volumes, data sizes, algorithms, and all of that. And this is, so yeah, this is the boring view of what's available. This is the pretty view, like here's some data, you know, example continuum, example H1 source. Now there are higher order H1 data products coming for this. This is all work done by Kelly Hess on the Spanish SRC, or proto-SRC in fact. So this is one of the PI projects that Javi showed. So for about half our survey area for a limited velocity range, but the range where most of the galaxies are directly detected, she's run source finding, found about 4,000 sources. We do plan, and this is an example of the sorts of data products and images that she produces. Nice H1 intensity maps, velocity fields, position velocity slice. There are kubelets to go to. We do plan to make this all public. We're starting to talk about it. The reality is it'll be 2025 at earliest, I would say, given that next year, almost here, is 2024, and we have to do this other data release first. But doesn't mean that you can't, data's not available to use if you want to explore, think about synergies. I mean, really, contact Kelly, she's the one who has all this data. But for sort of official collaboration, when it reaches beyond an exploration stage, I need to be looped into that. So then I wanted to talk about MIGHTY. And then my bias here is these are the surveys I am most involved with. But also, so MIGHTY is one of the large survey programs running on MeerKAT. And so MeerKAT, of course, I think is an important facility to think about for you, because it is the direct precursor to SKA Mid. It will become part of SKA Mid. So if you're thinking about what can we do in the future with SKA, exploring what you can do with MeerKAT is a natural step there. Again, simultaneous continuum in H1. The reason I selected this one of all the large survey programs is it's taking well-known extragalactic fields, and 2 of them are equatorial. I had thought that maybe this would be interesting based on yesterday's discussion. Maybe it's harder than I would have thought. Maybe you don't really like the equator, but I still might be the best compromise in the end, right? So I think what's nice here, this is from Natasha, the survey, H1 survey paper for the H1 component, and looking at predicted numbers of galaxies. This hashed region in redshift from about 0.1 to about 0.2, 0.25, this is the terrible RFI region. It destroyed us for Aperitif. It's almost as bad for MeerKAT, even though it's a more isolated site. This is mostly satellites. This is mostly GPS satellites. Satellites affect everyone, no matter how remote you go. Unfortunately, it's a redshift range where there's so many galaxies, because the histogram at the bottom, the on-filled histogram is sort of, you sort of assume that we could observe everything beautifully. And the filled histogram is if you assume that whole redshift range is lost. And you see that it's just taking out all these galaxies. It's just, yeah, very unfortunate. Okay, so there's early science data for MIGHTY. And this was taken with limited velocity resolution. So it was basically before the correlator was fully ready. Conveniently, this early interest for JCAM or JCAM Plus and JPass. It's available within the collaboration, which is an open collaboration. So like they invite people to join if you, and I can talk more about that. H1 catalog, there's deep data, deep HSC data. So there's a photometry available for these sources also. There is also full science data coming soon. So this is just the Cosmos field. Ian Haywood has led the processing of that data. I've seen a version of the paper. I'm not sharing anything from it yet because I didn't ask in time and I don't know what the status is. But it'll be full spectral resolution and sensitivity. You can see the Cosmos footprint from the early science data on the right there. The full science data is basically the same, except instead of a single pointing, it's a very close packed mosaic, and it has the full spectral resolution. It will be split into 2 frequencies. By infected portion where so many of our galaxies are probably at. It'll be different angular resolutions. Okay. And this release that's coming is going to be the cubes. So it's not going to be any source finding any individual H1 galaxy products, but they'll be there. Cubes are also great if you want to say, take your position of your optically selected galaxies and look for upper limits or do stacking or something. Okay, so 5 minutes, many other surveys to talk about, plus the idea of some science synergies. So we'll see how we go. Lots of surveys happening with ASCAP. They'll serve all their data products through CASDA. They have really strong plans for how things that are processed by their pipeline automatically get put in the archive and become available. Science teams will put in higher level data products also. The reason I didn't talk about it so much or focus so much is even Wallaby, which was all sky, is not going to be 100% all sky now. And this is their little bit of northern strip above the equator. It doesn't go super far. And if you look at this screenshot from their survey page, the red are things that they'll observe later because they're going to be harder to calibrate. And so they're doing the green and blue first, which are basically fields that they can calibrate more easily while they improve their pipelines. So they're not getting to the parts that might be interesting for you for quite a while. There are also many other large survey programs with MeerKAT. All of the large survey programs are going to make science-ready data products available. That's an obligation to the survey teams. And the South African Observatory is working very hard with the teams to make sure that happens. So Mongoose is targeted observations of nearby galaxies, beautiful, exquisite, deep data. I think their most northern galaxy is -10 in DEC. So that's why I left it out. MALS is targeting bright continuum sources for H1. All of these pointings are where they'll look, all these black dots. So there are some between 0 and 20 degrees in DEC. Their data will also be public, and they're focused on the absorption, but they'll image the whole field of view too. But it's a little bit more scattershot. You know, it's not doing a uniform survey in the way we think about it for imaging. And I don't go to the status. The Laduma is a deep field far south. You're not going to point at it. I think it's the extended Chandra deep field south. There's also a lot happening in the northern hemisphere, which might also be more relevant or interesting. So FAST, beautiful giant single dish. So unresolved, but will be basically providing alfalfa, but over more sky and deeper. The GMRT in India, they focus a bit more on lower frequencies, and so they've done some work doing stacking at redshift 1 and doing some nice fields, deep 2 fields. CHORD is a plan to expand CHIME in Canada into the US a bit, but it also means expanding it to higher frequencies. So it'll be H1 and emission, also unresolved. And then NG-VLA, expanding the next generation VLA, and DSA 2000 are some things that are happening in the US that could potentially be very interesting for H1, especially DSA 2000 could be all sky, continuum, and H1. Okay, so I don't have much time left. I wanted to talk about some possible synergies as I saw them. We have already had some great talks on this. Rosa gave a really great overview yesterday, so I was trying to think about what are things we haven't talked about, what would my interest be, and it could be I'm off base. I do not know what happened there. Wow. Yeah, this is why you're supposed to turn off the Wi-Fi before you start presenting, right? Well, it could have been way worse things that could have popped up or happened, right? So I can't be too upset about that one. And you got to see where Kelly was sharing stuff with me in our Slack. Okay. Things I'm interested in, I could be off base on what's possible with JPass and J+. Tell me that if I'm off base. So we talked a bit about star formation already. That's a natural thing to combine star formation and gas. I'm really interested in the fact that it's H alpha for star formation, and especially thinking about the fact that we also have radio continuum, which is a different star formation tracer on different time scales. So this is something I'm interested in, especially because I care about dwarf galaxies. As we go down to these low star formation regimes, do these tracers work in the same way? Do they continue to trace each other, or do we see stochastic star formation? So I had a master's student who used WISE data compare against radio continuum, but I think adding in H alpha, J+, this is something I'm excited about. I've written about in proposals in the past. I think H1 scaling relations, or other scaling relations, but if you think about the H1 synergies, those that require H1. So what happens at the low mass end in these relations? Is the scatter the same? Does it increase? Or can we see evolution of these scaling relations? Now again, for H1, the redshift range over which we're talking about scaling might be, or evolution might be a bit different than you think about it typically. This is an example from mighty early science data where Anastasia looked at the baryonic Tully Fisher, baryonic mass versus rotation velocity in two redshift bins. Not huge difference in those redshifts, but just sort of showing what we might do in the future. There's also been, I think, really interesting work by students I've worked with, showing that there's these ultra diffuse galaxies, very low surface brightness galaxies, appear to lie off this relationship. We see that in the upper right plot, those yellow stars that are off the baryonic Tully Fisher. And so I'm working with a PhD student now where we use the aperitif data. So rather than targeting things for extreme optical properties, having H1 data across dwarf galaxies to see if we can sort of see, is it a dichotomy or a spread across this? You know, here, of course, we can see where we're coming between JPass and H1, that we're adding the different components of this axis together. Maybe also angular momentum, specific angular momentum mass. Maybe there's some interesting stuff there. I know a bit less about this, but you know, trying to think of ideas, I throw some out there. And then I think exploring the faint universe. So this is something I'm very interested in, whether it's dwarf galaxies or low surface brightness, or especially low surface brightness dwarf galaxies. And understanding the H1 versus optically selected population. And so I'm doing this a bit with some mighty early science data, trying to explore this, saying, well, here are some optically selected galaxies. We don't really detect many of them in H1, but there's also all the H1 detections. Are any of those meet the same low surface brightness criteria and were missed in the optical work? And it does kind of look like there's about equal numbers in this field. Still very preliminary work that I'm in the middle of, so no strong conclusions, but sort of what can we learn from these two populations, and can JPass actually really help with this? Because we'll have, you know, can we get some reasonable photo Z's with this beautiful data, even for low surface brightness galaxies, so that we can put them H1 and gas-rich and non-gas-rich populations still have distances and put them on physical properties rather than observed properties. Okay, so some key points, final points. I had summary or conclusions at first, and this all felt too definitive. I think we all sort of agree that there's some great complementary between neutral hydrogen and JPass and J+ surveys. There's lots we can do. I also want to make the point, I think we've already had this, that radio continuum comes with most of these neutral hydrogen surveys, is also great. It gives us star formation. It can also give, that's what I care about. I guess there's also these things called AGN in galaxies that have radio emission. Neutral hydrogen is wonderful. I can tell you all about why it's great, but it does have its own complications that I think are limitations that are important to know in this context. So there's a lot of potential synergies. My kind of takeaways have been that the sky overlap with SKA is sounding like it's going to be a bit of a challenge. MeerKAT does have open time, so they'll have an open call probably in May-ish next year. And that's a possibility, something to think about, you know, proposing for something to test out or explore synergies with existing JPass or J+ data, but also doing JCAM observations of equatorial region so that you are, figuring out how to compromise and bring the two facilities into the different hemispheres together. I also wanted to highlight like opportunities or encourage people to think about things and getting involved. So join an SKA science working group. They're open. You contact the chairs, they're listed on the website. Like I said, I co-chair the H1 currently. You know, the working groups, like that means you make sure you get updates from the office about things. The working groups organize activities or meetings or get-togethers to discuss stuff. And you just are sort of connected and know what's happening. Or you can ignore the emails like all the other emails you ignore, right? There's no cost to signing up. It's just an extra email to delete in a worst case scenario. And then use the SKA Pathfinder data. You know, there's public data available, or join a survey team. A lot of these surveys have collaborations you can join. They have different policies. I know a fair bit about most of them, so I can answer questions. And just to advertise, because I'm here, I'm chairing a symposium at the General Assembly on neutral hydrogen in and around galaxies in the SKA era. And we also really do want the multi-wavelength view also, not just for H1 people, but to, what H1 can do for everyone. So when it's time, or if you're going to go to the General Assembly, keep that in mind. Okay, so I don't know how I am on time. I know we're also very behind, but I'm done.
Okay, great.
My apologies to everyone for that.
Yeah, thank you a lot for the great talk. Good on time, so we have time for 1 or 2 questions. Yep. Javier?
I'm very excited about the overlap between the aperture survey and impasse. And I was wondering, I have a lot of questions, but I will let them for the discussion. I'm wondering about the sensitivity in surface brightness or in surface mass of this survey.
Yeah, so again, it depends a bit, but it's around, I'm trying to remember what I calculated. I think it was a 4 sigma I calculated. It's around 2 times 10 to the 20. So we're detecting the main H1 disk in most cases. We also make, Kelly makes data products not just at our full angular resolution, but smoothed to a 40 arcsecond resolution. And that gives you much better surface brightness sensitivity at the cost of spatial resolution. So for most cases, the data, maybe you can start to see lower column density and some interactions. But in general, it's just the main H1 disk.
And in terms of mass, around 10 to the 7.
Oh, I mean, the mass depends on the distance. That's why I don't give it so much.
Okay.
Yes.
Well,
I think I actually have a plot from Kelly that I meant to pull and forgot. It might be in that Slack that I brought up actually, that shows the mass as a function of distance. That we call it a span power diagram. But I mean, I'm also happy to talk more later or prepare something for a discussion. So.
Can you go back to the slide of the mighty survey with the one where you show the effect of the radio interferences?
Yes.
So I understand that this is going to affect any survey.
Yes.
So looking at the lower plot, we should focus only on very massive or low mass galaxies. Is that the message?
Well, it could be. I mean, yeah, you could think about that in terms of science that around an M star. Argue for a low mass galaxy that focuses on low redshift or local universe, or you want to look at higher redshifts, in which case you're only going to detect the most massive things. Now, of course, with the SKA, that this will hopefully change because we'll still be out in this redshift range, but with more sensitivity, right? And so then we'll detect lower masses.
More sources at the knee of the
Yeah,
mass
yeah.
function.
But yeah, I mean, I think right now, if you're thinking about the science, you're thinking about, I think this is really important to realize that the redshift range is pretty much inaccessible. So you're either talking local universe, which is what I love, and then the real gain is going to low masses, I think, or you're talking about higher redshift, and then you're going to be limited to the highest masses by sensitivity right now.
Last question.
And do you think the H1 galaxies will obey the barometric tidal relation?
Do I think they'll? Yeah, I mean, I think almost all of them do. We don't understand is sort of the low mass end. Is there more scatter there or not, or what happens? We don't actually know what to expect. I think these ultra diffuse galaxies that scatter off of it, we also don't really know what to expect, and we don't have enough of them right now to sort of say and check all the systematics. So I think almost all the galaxies will follow it. If there's a population that falls off it, I don't think it's going to be the H1 properties that drive that. I think it'll be something else, or connected. It'll be a bigger picture thing.
Do you think we will observe more ultra diffuse H1 galaxies?
Yes. Oh, I mean, we're absolutely going to get more of those from the upcoming surveys.
Thank you.
Okay, great. I think it's time to go to the next speaker. Let's thank
So the next speaker is Rubén García-Benito. Transformation rate and H1 content of Galaxies. So
Hello,
Rubén,
can you hear me?
yeah, and we see your screen perfectly.
Okay.
So I will let you know when you are 5 minutes left.
Okay, thank you very much. Also, let me know if you don't hear me because we have, at least from my part, from my side, some hiccups on the other side.
Can you raise your microphone volume?
Okay, how about this? Can you?
Yeah.
Much better, yes.
Okay, okay. Okay, so I am Rubén García-Benito from the Instituto de Andalucía, Astrofísica de Andalucía. Sorry, I couldn't be there. And I want to present the JAGUARS. So the purpose of this talk, I have three main objectives. The first one is to provide a concrete footprint for a survey. I know it's going to be challenging because of the discussion we had yesterday, but at least I wanted to provide some concrete area of the sky. Secondly, I wanted to provide also some additional science that JPass could excel at, in addition to the already very comprehensive overview that Rosa gave yesterday on galaxy evolution, and also Betsey that gave just a few minutes ago. And third, why not to provide a name for a survey, following the idea that it's better to give to your project a name to ensure that it sticks to people's mind. So if some of these three main objectives remains after the discussion of this meeting, I will have fulfilled the purpose of this talk. So the idea is to first to give the name JAGUARS, or JAVALAMBRE Galaxy Unveiling for Advanced Research, and why not to add the S with SKA, so it would be JAGUARS, and I mean SKA, and of course pathfinders. So I think I don't have to tell to the audience how important have been the recent integral field spectroscopy surveys for the advance of knowledge that we have on galaxy evolution. In particular, the ones we've worked at the IAA with CALIFA. Here you have some of the main characteristics. I want to focus on two of them. First, the coverage of the galaxies that have gone from 1 effective radio up to 2.5 effective radio for the CALIFA ones. And the second one is the spatial resolution. In particular, the full width half maximum for the spatial resolution, which is about, for the these three surveys, about 2.5 arcseconds. I will remind this later on the next slides. So just a brief summary of already Rosa told yesterday about many things that we have done with integral field spectroscopy surveys, or IFU-like surveys. Since we have from the stellar populations studies, from the initial raw data from the data cube, we can build many different data cubes from all the hyperspace parameter of the physical properties that we obtain. For example, in this case, the mass growth, we can get a data cube from the mass growth in time from the galaxy. And some of the results that we already know from CALIFA is this inside-out growth. So from this mass growth, we can separate, just focus on the right side. We can tell how different parts of the galaxy grow. In the red box plot, you see the time assembly for the inner parts, and on the blue box plots, you have the outer parts. And you see that the time assembly for the inner parts is always older. So we see here, regardless of the mass bin or the surface mass density bin, the inner parts are older, or have growth older in time. And also, we can also provide products in terms that they could be very useful for simulations or for theory. Like, for example, this is the first time that We provide spatially resolved mass to light ratios for different types of galaxies. This is something that JPass already could done in a much better way for the spatially resolved part that I will also explain a bit later. Let me just finish with the very recent integral field spectroscopy survey that we're carrying out in Calar Alto. In particular, the Calar Alto Boy Integral Field Treasury Survey, CAVITY, which is led by Isabel Perez at the University of Granada. And the idea, the focus of this project is to study the environment influence of mass assembly of galaxies inhabiting the less dense parts of the universe, the voids, and study dependence of the galaxy formation and properties of these galaxies on larger scale environments, and to compare voids with other parts, larger scale structures. This sample was curated so that it could be observed from Calar Alto, and we are already gathering data. I just will tell just this result that was published this year, and it's about a comparison of the mass assembly of void galaxies and compared to other large-scale structures like filaments and walls and clusters. And just the results is very evident. So galaxies in void assemble their mass, their stars slowly. Here you have the time at the time that the galaxies assemble their mass, and compare to filaments and walls and clusters. And you see that for each time, each look back time, void galaxies assemble their mass slowly. Okay. This is about this recent integral field spectroscopy surveys, and in a very nice summary by Sebastian Sanchez, gathers all the information we obtained in the last years from these IFU surveys. And we see that the evolution of the galaxies is governed by these local properties, but affected by global ones. But the key point here, I'm not going to discuss all of this, is that these scaling relations that have these local counterparts are verified at kiloparsec scales. Okay, this is the size, the spatial scale that we are proving on these surveys. So I want to focus here on the spatial resolution. These surveys are around 2.5 arseconds. But JPass could go much better into this because of the JPCam camera. We have this 0.24 arseconds per pixel. Even if you go to the 2x2 pin, it will be much better. So I think this is an edge to the already very nice science that we have seen from Rosa and Betsey and the others on more or less nearby or far universe. This is something that JPCam or JPass could excel at. It's at the very nearby universe. Rosa already told that we can do with the comparison between JPass and IFU surveys. In this case, we did this job at the IAA of comparing this manga galaxy, and the results were very nice. But here is the thing that we can improve with JPass is that we can go very much further in the space. As I said, these surveys, these IFU surveys, they go up to from 1 to up to 2.5 effective radii. With JPass, we could go much further in covering the whole galaxy. But I'm going to focus here on an additional niche that I think JPass could excel at, even if only for a few bunch of galaxies. It's the very local universe. And here I'm going to touch also the H1. This is a work we did over a decade ago, but I think it's important. So we wanted to study part of star-forming galaxies, big star-forming galaxies, to study one part. If you look at this galaxy, you would say, okay, interesting region. So I would go for the very nice big spiral arms. But you wouldn't go perhaps to this very isolated, bright, but isolated one. But if you plot the H1 contours, then you see that you have a very nice coverage of H1. So we went to study this part of the galaxy, which was isolated that you would probably have missed. So this is NEC 5471, which is an H2 giant H2 region. So it could be always considered a very low massive galaxy, but it's a giant H2 region attached to M101. And you see it's very big one. It's over 600 parsecs. You see beautiful different clusters. But the difference that we did here, the study, in addition to the classical study of integrated properties of the clusters, we did for the first time, or one of the first times, we could derive the CMD, the color magnitude diagram, and provide the star formation history for a giant H2 region. And thanks to this, we could derive the star formation history and see that this giant H2 region was building up the stars of continued. It has a continuous star formation over the last 100 mega years. Okay. Continuing with this, we did another study on NGC 6781, which is at 3.6 megaparsecs. And here we did one of the first studies comparing both different star formation histories coming from very different data sets and methods. First, we gather a spectroscopy, and also we got also data from the stellar photometry. And then we did a comparison on the star formation histories derived from the color magnitude diagram and from the full spectral fitting. And this was a proof that both methods was, on the average, they were providing very good, similar results. But I think this is something that JPass could excel at for the very nearby galaxies. This job was extended in a very clever way with this method of using IFU for doing stellar photometry. Here you have an example with MUSE, with NEC 300, and using MUSE with the 0.2 arc-second per pixel, which could be similar to JPass. This could be also done with if it use the binning 2x2. And here they are recovering from the IFU. They are recovering the stellar photometry and then doing a stellar classification. So it's much better than you have the CMD, the color magnitude diagram, but also you have the spectroscopy, the spectra from the stars, and you can do a very detailed analysis of the stellar populations. And I think this is something that could be done with JPass, and even if it's only for a few galaxies. But it's a niche that I think it could be exploited. Yeah, so Rubén, just in the last, yes.
Your voice is low. Can you?
Okay, sorry for that. Okay. So in the last 2 minutes, I want just to give the last two main objectives is just to provide a concrete footprint and a name. So this and why not a nice logo for the survey. So these I'm gonna here just focus on the very nearby universe. I mean, in addition to this, we will have the local and the far universe. So I'm gonna here present only just the objects that we have in the very near universe. So I use these catalogs, the local volume catalog, the extended Vigo cluster catalog, the cosmic void catalog, the net local volume which extends the local volume catalog, and all of these only for the very nearby galaxies, and also the recent published Eurosita final equatorial depth survey, which has many extra resources in an area. I don't have to remind you the importance of having H1, and this was a very successful survey. The Viva sample, which only with 50 galaxies with H1, it could be they did a very nice job because it was selecting galaxies with different H1 morphologies. This is something that it's now with Apertive doing, and I'm also in with Apertive, and it will be very cool to have all of these H1 galaxies also with in combination with JPass. So again, I'm gonna here just plotting into this concrete area of the sky in this footprint of JAGUARS, the nearby objects that are extracted from these catalogs. And in addition, you will have obviously the far universe ones. This is just some examples of the very nearby galaxies. And in addition to what I explained, we could do from the from these galaxies, something that we couldn't do in Khalifa, for example, because of the spatial resolution, is that we can study the stellar populations across the disk on the highness, on the depth of the disk. This is something nice that it could be done with JPass. So this is the concrete. Yeah, just finishing. So this is the footprint. Is in this area of the equatorial plane. It has the big chunk is around 1,500 square degrees, and there you have the 200 square degrees that it's covering the EFITS, the Iversita Field Equatorial Plane Survey. And here you have an idea of all the objects that we have from the local universe, from very big galaxies and the local universe, to also void galaxy that would be very nice to explore. And this Iversita, which is in the triangles, I have selected only around 600 sources in X-rays that are very extended. So here is the size of these objects from 30 arc-minutes, like this very big galaxy, to something like 1 arc-minute. We have in the Iversita catalog sources extended in X-ray up to over a few 1 arc-minute. So it would be very nice to have the optical counterpart, and why not the H1 one. Also, I have some details on the different type of galaxies for these sources. So I will end up here with this proposal of a survey, of a footprint, also of a concrete niche of science that also JPass could do. So that's for everything from my side, and I'm ready to take any questions.
Thank you very much, Rubén. Do we have some questions also from the virtual participants? Renato?
It's a little bit more, perhaps an update. Ruben, can you show me the last slide that you showed, the one that you showed the EFADs? And yes, so the green, the red, and the blue rectangles there, are they supposed to be the JPass footprint?
Right.
Okay, so well, they may not be completely updated with the version there's there. Maybe Ali can confirm that. I think that the lower limit there is about 20 for the second tier. In your case, it's going all the way to 10. So, well, I'm not delivering bad news. I'm just saying that, you know, this is, if I'm right.
Sorry, I have some hiccups on the audio side, so
We check. If not, we can let this for the discussion.
Let's leave this for the discussion.
okay.
The good news is Cosmos is not too bad. I was commenting this before. Cosmos is not too bad. It's bad for JPass. You cannot include it in the JPass footprint. It wouldn't make sense. But having a proposal to observe Cosmos, that would make sense. I can expand on this later.
Great. So let's thanks Rubén again, and let's go
Thank
with
you.
the next speaker. So the next speaker is Renato Dupke, that's going to tell us about exploring the scene.
Right there.
It's also
This with the arrow. This, okay. Oops, I guess I moved already. No, but then, the next one is this one, and then you advance or then you go back. All right.
so you have 20 minutes. I will let you know when you are.
All right. Okay. Hi, everybody. So, listen, I'm Ricardo Dupke. I'm the representative of the National Observatory in JPass, and I serve together with JAVALAMBRE as a science director. Well, before I start, I'd like to thank Pepe, Javier, and Marilu for the invitation to come here and made me only miss the first part of the first day, but not everything. And also Silvia, Bonal, Alessandro, and the Rakuten and Rodrigo from Martins for sending some material in the last minute for this presentation. So I was asked to talk a little bit about the agreements that we have, the partnership with different collaborations and groups. And so I'm not going to repeat, probably, I don't know exactly what was talked about. You know by now this JPass has at least 4 Cs that are being observed. The science array field has been finished. And this is called the Stefan Quintet's field is pretty much finished as well. I'm not sure about the status. You may actually know more than me because probably we worked there in the first day. Just to make it something that might be useful for a discussion later that was mentioned yesterday. I changed a few things in my talk based on the conversation we had yesterday. So up to, let's say, this is a little bit focus for me. 6 by 6 pointing square, you get 0.5 square degrees. So in the beginning, it's very inefficient. That's why going to some place for a particular small target may be not the best thing to do. And then you go into the phase of rapid growth. So we have, and of course, since we already started, even though most of this, the last agreement we have now with the Agility Steve Pro's team, that was March of this year, but it's time now that we're growing to increase the agreements that we have with other collaborations to optimize the science that we get from different wavelengths and different precisions, different data sets that we can join to do the exploitation together. So the first one I'm going to mention Renato talked a little bit before me, and he was talking about the EFADs. Right now, the EFADs is the only field that has actually full depth of the whole survey. You know, the EROSITA has stopped after half coverage. There's 2 more years to go to complete. It's unclear exactly when it's going to go back to observing. So about this, the EFADs, the 140 square degrees, they have an incredible number of cluster candidates, at least in groups, more than 500, and with a purity of 80%. And in general, they have more than 1.3 thousand clusters and 1 million AGMs found in half a sky, the German half of the sky. So this is one of the things. I'm not going to be talking about things that everyone has been talking about. It's all amazing, but everyone already has heard about this a lot. And one of the things that I think is very interesting is the ability to quantify the energetics that you can find in clusters and groups of galaxies. This is one of the examples of EROSITA and actually a SKA here, where there's supposed to be a filament in this cluster to 9195, and they measured residual. Not so much, the halo was not that clear. It's not clear why there was not a strong halo here, but several different AGNs and injection of energetic electrons in the ICM. So one thing that should be mentioned is that this was the original thought that I actually brought to the Eurozeta meeting a long time ago when we were trying to do the agreement. That was our original hope to observe, because this is the SDSS, which I was pretty much having common with them was about 2,000 square degrees. Well, this is the most updated version that I put out there. And the dark blue areas here are the first tier one, the preferred ones, and the light blue are the tier 2. There was a tier 3, but I guess it was dropped because we're going to be dead before it happens, or something like that. And here is the Eurozeta German side. The area has become extremely limited. Well, much less is about 1,000 square degrees, and a lot of it is in the second tier. Okay, this is something that it's interesting for a conversation as well. If we can play with the tiers to see if we can optimize something around here. By the way, the EFEDs that was mentioned before Benito was there about here as well in this region. So one of the things that's very interesting is to see really the filaments, the electron reacceleration in the case of halos, and also the usual process, the Fermi-1 process of electrons, they're going back and forth in shockwaves with clusters formed by merging. So you have this kind of magnetohydrogen effects continuously happening. And also when they are accelerated by turbulence, by Fermi-2 processes. So we are very, very excited about even the areas being smaller to start working on that, because one of the interesting and power of JPass is based on mini JPass, the 1 square degree that we had, is the ability to detect systems with very low masses. And this is pretty unique of JPass because of the precision for Z. You can narrow down the system's clusters and groups with a very good precision and get rid of the issues with foreground, background systems, and so on. And this is one of the lattices richness, and this is the mass that we have for the clusters. There are different redshifts that can go to pretty high redshifts actually and detect the systems. And this is 10 to the 13 solar masses. Okay, so we have actually some, they're less than 10 to the 13 solar masses. And this is of course, there is you can always put some threshold on the significance. This is not the highest significance, but you can see that you can detect up to there. And even if you make the significance a little bit higher to 3 sigma in that particular plot, this by Matematuri, and the clusters here were detected with the Mikko code. You can see that you can still get the systems to pretty high redshift up there. The same thing, we have now basically 4 codes for cluster detection. The second one, and this is a paper is about to be submitted, and then you have the Aegis field X-ray sources in the BZ wave clusters, and this is the mass, and also you have a very nice detection up to redshift of 0.5 to 0.6.7, and this is going to be something. It's a very interesting field to explore. So we established a MOU for joint exploitation of the overlapping areas with Eurozeta. And there's a joint, basically something, so it's a joint committee that gets the projects, they're submitted from both sides, and they advertise and they deal with the process of developing the work. With the Russians, we were not extremely lucky, even though they were the first ones that actually got to talk to, but they were a little bit standoffish about making any kind of agreements, and who knows what's going to happen after that. The second one, I'm going to change a little bit the type of collaboration that we have, and this is a very small field of view, but it's interesting because there's an incredibly amount of coverage for that, which is the agreement, the most recent agreement that we have with the JWST NEP, North Ecliptic Pole, time domain field of JWST, which has a precursor, which was the HST observation of the same area in the sky for several years. And the reason for that particular pointing, which is the net field, is that it's one of the places that you can have continuous viewing zone by JAVALAMbre. So you can go there and do variable sources, transient sources really well. So the area is small, it's about 14 square meters here. This is 2 arcminutes for the Hubble, the pointings they have there. And we went there, this proposal actually started inside JPass. The PIs, they came and Rolf Jensen and Grisville, when they came and thought it was a good idea, we proposed this project inside, and we got it to observe it has the same filters of JPass, and it's a little bit deeper than JPass. So this data, well, this is just a history of events. So they were successful in getting the HST proposal for that before, and then we got this within JPass, and there were 2 more Hubble proposals called Treasure Hunt then, and now it's called the HLST is called Pearls. So the good thing about this field is that it has an incredible amount of ancillary data. See Subaru, some LOFAR here, that's where I remember the name of Van Veren, is that right? Data for their region, and of course JPass and so on. So this data is almost pretty much everything is almost observed. Maybe Chandra is not yet completed, and the first works are starting to happen. One of the things that was good for us for the JPass with this collaboration as well was that one of the PIs, Francesco Silvano, shared the XMM data with us, which was very important to calibrate the detection of clusters in JNAP. So the photozy calibration with their data, part of spectroscopic data was done by Antonio Cavalier. And there are 2 papers about to be submitted now. One of them is transients. O'Brien and all. They found 12 transients there over 5 years, and perhaps they've been comparing with the photozis that have JPass. They also are using photozis from JAVALAMbre. And a very recent paper as well by Chao and Francesco Silvano on the XML observations for variable sources and detections, and they're using also JPass for the optical components. So as of yesterday, as a matter of fact, or no, yeah, I think it's yesterday before yesterday, there are 2 more catalogs for clusters in that region, one by Ted Putma, is here, and one for Paulo Lopes using environmental isolation. They have been added to the other 4, and as well as Raza's catalog for stellar masses, and they're available in the week. So this is going to probably expand. We have CLA. He has been a major person in the Akari observations of the actual NAP field, which is very interesting. It has superclusters, lots of interesting targets there, and has an extensive amount of infrared data. And this is one of another possibilities that we have to do proposals for JPass. It's a little bit off the footprint of JPass to the north, but one of the ones that can be used for the transit folks, transit working group in JPass as well. And we hope to be studying how to close them. The other collaboration that we have for quite a while is the Weave QSO. There's one of the ones that was asking yesterday about if we have an agreement with SKA, do we do the agreement with SKA itself or within a science working group within SKA independently, if they have the freedom to do this kind of things. And in the case of the Weave, they did. And their interest in the QSO is that JPass can go there first and tell them where to point the fibers, because JPass can very fast detect if it's a QSO or not, and that would significantly increase, or it was effective too. And The advantage for this is that they're interested in measuring large-scale structure and BEOs, for example, high redshift. The competition with DASI is not very good because this is a density of galaxies, redshift here, and luminous red galaxies are red and emission line of green. So if you compare, this is JPass, it falls relatively fast. The density at about a shift of 1, something like this. And DASI continues faster than redshifts, but when you go to quasars, the situation is different. And you can actually be, well, competitive and get information here with quasar high redshift. So this is right. So to go faster then. So this is the footprint of wave here. It's the same as the plot before, but now thanks for this plot. The red one here is what they have for wave now, and that's the original one. And this part here that was close to the equator also is not observed because of the efficiency issues with JPass so far. There are many papers on that already appeared, most of them by paper detection algorithms. So one thing that I'd like to throw it out there, which I think was interesting, I was thinking after I came actually to this meeting, is that one of the things that, and I mentioned before, that that SKA and MeerKAT, for example, has done this many times, is to detect this the energy injection of different types in clusters of galaxies. The many different types, from bubbles, from the AGN activity to cold fronts. This is a typical cold front cluster. The cold fronts can actually be creating mini halos, which are in clusters that have cold cores, and of course, shock fronts and reacceleration of electrons and mergers. And this is particularly interesting, like I mentioned before, because JPass will be detecting a lot of the systems, especially the groups, a lot of them for the first time, and the impact of the energetics of this energy injection in the ICM, the IGM of these groups is way more significant than in clusters. And this will be interesting to quantify that. That's a classical example here. Coma, I'm not going to enter details because you probably have seen this before. But it detects this is the radio halo, we're finding coma is a merging cluster. And there is also here, this image here is only the center, there's also here relic, re-accelerated electrons due to this merger. Interesting enough, we noticed this also in looking at the ICM. So this is important because, among other things, you can find out if the clusters are relaxed or not. And it's something that I've been a little bit obsessed about in separating them too, because clusters in JPass, they will be probably very good and competitive cosmological discriminator because of the numbers and because of the purity and so on. However, most of the systems that depend on to calculate the mass, they depend on virialization, relaxation of the systems, and this is very difficult to access, especially high redshifts. You cannot point an X-ray telescope and wait forever to actually get the substructure there. Sometimes you can. The next generation of X-ray satellites like Axis or Athena and so on, they're going to be doing this, but it's going to be in the 30s. So in this, the problem is that the people use the Hertzsprung equilibrium equation, which comes from the Euler's equation. You have to get all this velocity motion of the gas out. If not, you have a component that you don't know, and you don't get the masses correctly, which is important for cosmology. So one of the things that is interesting is there are two approaches there. One is we have enough numbers now that we can change number of systems by purity of what I'm looking at and select the relaxed ones. Throw away the merging ones. If you have hundreds of thousands, you have tens of thousands of clusters, you can do that. The question, how do you know they're merging without the X-ray obvious imaging? One of the things that I've been doing with Yuri Jimenez-Terra, in this case here in the ICL of clusters, the particular markers that you can see in the optical that indicate the clusters are merging or they're relaxed. And this is interesting because, for example, in this case here, people just tend to assume the clusters are merging, relaxed at high redshift, because of geometrical constraints, offset of BCG and so on, and ellipsoids and other stuff. And then they apply standard equations that have been calibrated for clusters that are relaxed nearby. And sometimes this can lead to errors. And this is one months et al. They have been, the group of Steve Allen have been doing this work for a while. It's a great work. And this is just showing the difference in precision when you add, this is the latest work, they add like 2 high redshift clusters. And they improved the precision by 40%. So these clusters are very important, right? They're using mass fraction. They depend on the clusters being relaxed. You already have found this in one of the clusters, indicating merging. So in the X-ray, this had just enough counts to be able to see this huge incoming thing from this direction. So this cluster is not merging. So this is just highlights the importance of this work. Okay. So okay, this is for discussion, but I'll just put it very fast here so you can think about this gray region here that you didn't notice before is what I estimate to be the SKA mid-JPath declination, which was 40, maximum 40. What would be better, that was 20, right? That was said. So this is the 40. And this is the plot that I showed before, and this is the JPath footprint. So by eye, and Alessandro can do this more precisely, I was just by eye calculating the area here. In this particular case, for tier 1, there would be 900 square degrees, and a lot of them for tiers 1 and 2 altogether. If you use the desirable one, like significantly less, and give a 10-20%, because I'm doing this by eye yes in the hotel. So for tier 1 or 1800, a lot for tier 2 as well. If we got something like that. Now I'm gonna lower a little bit. That's the second one for SK1 with 10 degrees, which would be the desirable is 10, and it could go up to 20. Oops, I guess it's too much. Okay, that's the one. So this is 20 degrees. So you got this region. Most of it is gonna, you still get some tier 1 systems, and of course the tier 2, but they are not in the main area of JPath. I'm not sure exactly how this, I'm assuming that this is going to be slightly less efficient than this region, but I don't know, Ali can tell me later. So the possible one is a small number of 180 square degrees for tier 1 and 1800 for tier 1 and 2. And desirable would be nothing for tier 1 and only 900 square degrees for tier 2. They'll have. And of course, the SKA low, if you go to below 10 degrees, you only have this 900 degrees in tier 2, and tier 2, assuming probably, right, they'll take more time to be covered. Okay. So, yeah, so I think I'm going to finish here. And thank you.
So time for one very quick question.
Thanks, Renato. Well, I'm allowed to ask one question, so I'll go to the straight one. I like the plot that you showed with Yoli. Are you showing that clusters with high fraction of ICL, the cluster light, are merging, and those with low?
Yes, thanks for asking. It would take too long to explain this in the time that I have. So this is actually ICL fraction. So it's the ICL in a particular filter divided by the total light, ICL plus galaxies. Okay, so this is where the feature appears very clearly. And those are many clusters. We started with a few, we are growing, and so far the success has been 100%. The number is not hundreds. And so the clusters that are supposed to be relaxed fall in this blue region here, and the ones that have different signs of merger, independent signs of merger, they're in the red, and they have this particular excess that called blue excess, but now I changed the name because for high redshift clusters, including some high redshift, it seems like the blue becomes redshifted. So it's just an excess of ICL.
Like here, you're plotting against wavelengths, right? And I guess this.
Yes, that's wavelength. Sorry, rest frame. Yes,
Rest frame,
okay. And this is the equivalent spectral type. So it's around IF stars, And that's why we interpret this as being, since they are merging, as being the removal of the stars from the outskirts of galaxies that supposedly have more of a flow. I'll say the spectral type, Raza, they say there's a different age in chemistry than there was in the center. So they are kind of younger in the outskirts and then in the internal part. So they are disrupted and you have the sudden throw of the stars AF that will live about 2-3 years, and then they got disappeared, becoming white dwarf. By the way, looking for white dwarfs is something interesting that can be done as well. That's the scenario that we're going with so far. But this is a merger. And the thing is that with the SKA, detecting in this a huge number of clusters, if there's a halo, because if halo is a marker for a merger, you can already know there is, independent of what you can do with the physics of that particular system, you already can clean the sample from cosmology with a large number of systems. And that sounds pretty interesting.
Okay, so we will stop here. Let's thank Renato again. So we are going to have a shorter break, just about 15 minutes. So we will be back here at 11:45 time, local time, and for the galactic time, and for the virtual participants. So yeah, basically we will be back in 15 minutes. So thank you all.
Hello everyone, welcome back. I'm Rahna. I'm a postdoc at SKA. I'll be chairing this section. We have 4 speakers in this section. Our first speaker is Amidou Sorgho. He will be talking about how does the environment affect the angular momentum of galaxies.
Thank you very much. Hopefully it's fine. Yeah, I'll be talking about something a bit more specific than what we've seen this morning.
It's my hand.
Okay. It's about the angular momentum of galaxies and especially isolated galaxies. I have to say that I'm very grateful for Betsey's talk because she covered all of the bases, more or less, of what I'm going to talk about. So it's a work that I've been doing at the IAA together with Lourdes, who is online, and Kelly, who recently left for Sweden. And yeah, other people like Ianja and the whole Amiga team, including Marilu and Teresa. Okay, I'm sorry, I didn't forget, it's a brain freeze. Okay, so yes, I'll try more or less, this is not the outline, but I'll try more or less to direct the scope of the talk to these. Basically, the connection between the angular momentum and the environment, and also going a bit more specifically and giving a bit of basics as to how we measure angular momentum, both in optical and in H1. And talk a bit about the complementarity between the H1 and optical, because that's the focus. And well, I'll also talk about, maybe not too much, but I'll try and mention something about the environment and how we can lay the scope for potential and projects between H1 and JPass. So you've seen this plot before, this figure from Rubén's talk, including this. So this is my attempt to kind of showcase the importance of the environment when it comes to H1, or the other way around, how we can use the H1 to probe the environment of galaxies. This is because the H1 is the external envelope, right? The most sensitive, most external component of the galaxy and the most sensitive to interactions. And this cluster here is the famous Virgo cluster. The contours are X-ray, but the individual galaxies here with the tails, with arrows, are the ones that are shown here. And what they basically say is that when the galaxies form or interact in the outskirts of the environment, then what happens is that the gas tends to be stripped away from the galaxy, forming forming H1 tails. And this is another example of NGC 4522, which is potentially falling inside, moving in a hot cluster, dense environment. And then the run pressure stripping basically the gas. One thing that we know is that the amount of H1 that you get in a galaxy, it's sitting in a dense environment, depends on how far the galaxy is from the core of that environment, being a cluster or a group, but mostly a cluster. And then this is quantified by the efficiency of the galaxy, meaning how much gas we are missing from the galaxy, missing in the galaxy from what is expected. And when you plot that as a function of the distance from the cluster, then you get a nice trend. The galaxies in the middle, in the center, being more efficient than the ones in the outside. So this then raise the question of what is the importance, or how does the angular momentum of galaxies behave in different environments? So I won't go too much into details in this slide. I try to put it in one slide because that's not really the focus of this meeting. But I wanted to show here, what I wanted to show here is basically giving you a kind of brief outline or brief idea of what the development of angular momentum study has been. So what we thought initially is that, well, galaxies, in the formation of galaxies, in the tidal talk theory, when gas forms, matter or baryon form inside the dark matter halo, basically what happens, because the matter follows the dark matter, the baryonic matter follows the dark matter, then they end up having the same specific angular momentum, which is basically the angular momentum per mass. And then in the recent years, there have been, with the availability of tools and poles, the many simulations have shown that, well, the picture is more complicated than that. Because, for example, when you go to high redshift galaxies, then there is basically virtually no correlation between the angular momentum and the H1, the mass of galaxies. So where we stand now is that, well, the angular momentum, the amount of angular momentum that a galaxy has is a bit more complicated than what we thought previously, with that content being subject to where the galaxy is, to the environment. In 83, where the angular momentum of galaxies observationally have been found to be correlated to the H1 to the total mass. I have to mention that this is the stellar angular momentum as a function of the stellar mass. So we see that depending on the population of a galaxy, be it a late type or early type, first of all, they all follow a trend, a linear correlation, but then the later galaxies tend to be shifted vertically compared to early type galaxies. So moving from that, but that was in the 80s. It wasn't until 2014 that the gas component has been included in the evaluation of the angular momentum. And the picture that we have now is that this correlation stands, even though the slope that was initially found is more or less, there is a broad range, there is no fixed number, but I'm sure 10 studies, I would say, where we get the baryonic angular momentum as a function of the baryonic mass for different types of galaxies. But one thing that's lacking from all these studies is that there is no strict selection in terms of environment. So it doesn't give a clear picture as to what the effect of environment is on that content. So that's what we've tried to do in this study using the Amiga sample. So Amiga stands for analysis of interstellar medium of isolated galaxies. And so the sample was built on an initial sample of isolated galaxies of a bit more than 1,000 galaxies. And there have been building and defining parameters for evaluating the isolation parameters of these galaxies. I'm showing two plots here that resume it all. This is a plot of the local number density as a function of the tidal strength for galaxies selected in different environments. And so you see the Amiga galaxies here in gray, and galaxies from compact groups and clusters. And what we see here is that there is a clear separation between the Amiga galaxies and those. And so since 2005, which was the initial, where the initial paper came out from UDES, there has been a lot of work to refine and broaden the amount of data that's available. So now we have a multi-wavelength data set of these galaxies ranging from radio continuum all the way to optical. And one thing that is important that I should mention here is that when we talk about isolated galaxies for Amiga, we are not really talking about field galaxies, because when you look at this plot here, there is a clear, this green line here shows a fit of the ratio of far infrared to blue light as a function of the blue light. The Amiga galaxies here are shown in a green line compared to galaxies of different environments, including field galaxies. And what we find is that the Amiga galaxies, them being isolated, they tend to present the very extremely low values for parameters that are usually affected by interactions. And I'm moving forward to showing a few more examples. This is the efficiency of the Amiga galaxies compared to galaxies from other environment, non-isolated mostly. And what we find is that the Amiga galaxies are a lot more deficient with a clear shift compared to those. This is the work from Mike, who was a postdoc also in working with Amiga from 2018. And also this work from Jamie Bock, 2020, shows the, I would say, an update of the star formation rate as a function of the mass, an update of the work that Rosa mentioned yesterday. So again, we see that the Amiga galaxies tend to separate themselves, behave differently from non-isolated galaxies. And moving forward and showing this work that's ongoing from another PhD in Amiga, Clara, which gives a comparison of the Amiga galaxies with other Hydra and other cluster galaxies. So given all this, what we did was to build a kind of model or a kind of scheme to select the Amiga galaxy. So we built on the initial sample that was available and ended up selecting 36 galaxies that have both H1 and optical data available. You might say, well, 36 is too small compared to the initial sample that was 950 here. But don't worry, make sure that this is representative of the whole sample. So here I'm showing again the local density as a function of the tidal forces and the Amiga galaxies that we selected. We see that most of them represent, apart from these guys here, they can tend to follow more or less the isolation criteria defined. And also as a function of distance and also morphology. They more or less are in the same range. So here, well, I won't talk too much about this, but this is the gas to stellar mass ratio, a function of the stellar mass, and compared to other galaxies in the literature. So to try and move quickly, because I think I'm falling behind. So when it comes to measuring the angular momentum of galaxies, like I said, we want the total baryonic angular momentum. And here we define the baryons as the mix of stars and gas. We are neglecting the H2, and for good reasons. So what we do is say that, well, the angular momentum is basically the sum of these two, of course, taking into account the gas fraction. And so what do we need? We need H1 to get the gas, and we need the stars, and we need optical data to get the stars. So this is the type of data that we use for the H1. What we're interested in is how do I say that, the data cubes, basically, H1 data cubes. And what we need from optical is the light curve, basically. So how do we do that in practice? We say, okay, we take the galaxy, we split. Most of you must be familiar, especially the H1 people must be familiar with this, the tethering model. So we kind of cut the galaxies into small ellipses, concentric ellipses, and in each ellipse, we work out what the angular momentum is. That's what I'm going to put in the talk. So basically what we do is that, okay, when we consider the gas, then we take the surface density of the gas, the velocity of the gas, and then, yeah, we plug in this very simple integral, and then we find the angular momentum. And the total angular momentum of the galaxy is basically the integral of everything, summing everything up, easy. So, again, in practice, what this guy is, the surface brightness is basically this curve here, right? This is for the H1, and that's for the optical. And V is given by the velocity, the rotation velocity. Ideally, what we want is to get the velocity of the gas, to get the angular momentum of the gas, and the velocity of the stars to get the angular momentum of the stars. But we don't have that because it requires that you have what do you call it? Kind of spectroscopy, optical spectroscopy of the galaxy, which is not easy to get. Yeah, I'll move quickly. So we approximate the velocity of the stars to be that of the gas, which is for many galaxies, especially big galaxies, this is a very good approximation. So moving quickly, I think I already mentioned this. So this is something that I want to keep for the discussions later. Allow me to skip that. And so what we find is that for the isolated galaxies, the angular momentum tends to be, again, this is the same plot. Baryonic angular momentum as a function of the baryonic mass for different samples of galaxies, but what we are interested in here are the isolated galaxies, the Amiga galaxies. We see that they tend to sit, here it's a bit difficult to see, but a zoom-in version is this. You can see that they tend to sit above, not a systematic shift, but they are nonetheless above the other galaxies, meaning that these isolated galaxies are getting at a given mass, they have more angular momentum than the non-isolated counterparts. The implication of that is, well, this is another plot, another set of plots to further prove that. Here we are taking the difference between the individual galaxies and the relation that we fit for the Amiga sample. And we see that many of them actually are below the zero line. And so now dividing into the two different components, gas and stars, we clearly see that there is no systematic shift. But what is interesting here is that we get a dependence of angular momentum with the fraction of gas. This is the color bar gives the fraction of gas that is available in the galaxy. And that relation is not new because already found in previous works, but it's nice to see that what we are getting here correlates with that. So I think this is more or less the overview that I wanted to give. And so I will leave you with these conclusions here, but I'll go. Yeah, I think the main point to take away from this is that the angular momentum, like we said, is basically for the Amiga galaxies, for the isolated galaxies, is higher than the non-isolated galaxies. And the reason for that is by definition, the Amiga galaxies are supposed to be isolated with no major interaction in the past more or less 3 gigayears. Meaning that when galaxies are isolated, no interaction at all, then what these results imply is that they tend to conserve more the angular momentum. And that's because when galaxies interact, it's obvious that whether they could either gain or lose angular momentum. It wasn't clear until now, but this tends to show that it's more likely that they lose than they gain. So let me stop here and put these slides in, which can be kept later for discussion. I'll stop.
Thank you.
So thank you very much. Regarding the Amiga sample, when you were talking about that, you said a measure of tidal strength. Can you elaborate on that?
Yes.
How do you define tidal strength?
The tidal strength is basically the sum of all the forces, external forces that are exerted on the galaxy by the neighbors. Roughly put, that's what it is. So you take a single galaxy, you measure you count the number of neighbors that it has. You can take different definitions, but you can measure up to 5, 10, or all the neighbors that they have in a certain radius, let's say 0.5 or half megaparsec. Then you count you evaluate the external forces that these galaxies exert on your galaxy of interest. That's what gives you the parameter. I didn't put it, but you call it Q. I call it Q. Yeah.
So just piggybacking this question, how do you define isolation?
The isolation is basically, let me go back to this slide here. Hopefully I find it quick. Yes. So the isolation is basically defined to be, so we look at this plot here and also other plots that I will put here, and we evaluate what is the cutoff of the tidal strength and the local number density for a galaxy to be considered isolated. In this case, we're looking at these two parameters. Like I said, the sample was built on the previous sample of isolated galaxies, 1,000. These were known to be isolated. But building on that, we say, okay, let's establish criteria for a galaxy to be isolated. So we evaluate the local number density and the tidal strength. And then we compare these to galaxies of all sorts, field galaxies, compact groups, and clusters. And then from there, we define the cutoff that we consider for these galaxies. So basically, it's a galaxy that, let's say, has a maximum of 3 or 5 neighbors in a certain radius. And apart from that, it has to be the neighbors have to be a certain size compared to the galaxy of interest. And putting all these parameters together, we get the tidal strength and the local number density, and then we can decide from there.
So you may have like galaxies that belongs to a cluster where it's out there right now, and then you use this parameter is isolated.
You can do that, but you will end up getting numbers that don't fall here. You will get high tidal strength and local number density. So you know that they are not really isolated in this definition.
Okay.
If I may add, just to say that we always explain that are isolated from major companions. And then we quantify the effect of minor companions because there is no such a thing like isolated or non-isolated. So these are isolated from major companions, and we try to quantify as good as possible the effect of the environment, but the environment of minor companions.
Thank you.
Okay, let's thanks again, Amidou. So we project Ianjamasimanana. And he will be talking about MeerKAT H1 observation of Hickson combat group. Roger, so you have 20 minutes, including 5 questions.
Hello everyone, I'm Roger, or Ianjamasimanana. I'm a postdoctoral fellow at the IAA. So I will be presenting a recent MeerKAT H1 observations of Hickson compact groups. So this is a proposal led by Lourdes Verdes Montenegro. And also this is a teamwork at the IAA. So my picture is here. So I'm leading the data reduction. And Amidou helping with the analysis, and SKA doing a very nice three-dimensional visualization of our data. So I would like to start by defining Hickson compact groups. So these are groups of galaxies composed of 4 to 10 members. Typically, so their centers, so the galaxies in their centers are tightly bound together. So interactions are very frequent in this in these groups. But surprisingly, the star formation efficiency and the CO content in these compact groups are similar to spiral galaxies. The star formation efficiency and CO content in of spiral galaxies in the field. So Verdes Montenegro in 2001 defined this evolutionary sequence in Hickson compact groups. So where in phase 1, most of the H1 is confined to the disk of the galaxies, and they are usually have undisturbed kinematics, and they move to phase 2 due to interactions in the galaxies, where a significant fraction of H1 sits outside of the galaxies in the forms of tidal features. So you can see here very long tails connecting these galaxies with these galaxies, for example. So this is a very nice example of phase 2 Hickson compact groups. And they evolve to phase 3, where almost all of the gas are removed from the galaxies, and they are either not detected or in the forms of features that are not associated with the individual galaxies. Okay, the GPT observations of 22 Hickson compact groups revealed hint of diffuse H1 emission in the 3 Hickson compact groups. So this is one of the idea of our of the MeerKAT proposal to detect those diffuse H1 component in phase 3 groups with MeerKAT. So this is this a spectrum, GPT spectrum, and the VLA spectrum in this Hickson compact group, one of the Hickson compact groups studied by the author. So this is one of the very recent papers about Hickson compact groups by a former postdocs at the IAA, Michael Jones. So he actually reduced all publicly available H1 VLA observations in a uniform way, and reclassified the H1 morphological phase of each group, and redefined the H1 deficiency of of the sample. So this is one of his results. One of the things that he did is to separate the H1 content that still belongs to the individual galaxies and any features that is not associated with the individual galaxies. So you have green and blue contours here. So the blue contours are H1 gas that is still associated with the individual galaxies, and the green are tidal features. So they did it using sophisticated three-dimensional visualizations. So this is phase one, okay? Where, like I said before, most of the H1 is confined in the groups. I think the red contours here are galaxies at different redshift. So these are phase two groups where, like I said before, most of the H1 are in the forms of features that are not associated with the individual galaxies. So you see large tidal features in HG 16, HG 31, and all these phase two groups. So another result from this paper is that the distribution of H1 deficiency in phase two and in phase one and phase two are similar. So well, despite very large H1 that is that is found in the intragroup medium, the group as a whole is not H1 deficient. So this is phase 3A. In phase 3A, there is no H1 emission detected, or they are in the form of intragroup medium gas. Okay. So, for example, the VLA failed to detect H1 in this very advanced phase of Hickson compact groups. But like I said before, GPT observations of orthocore found evidence of diffuse H1 emission in these galaxies that is spread over velocity of 1,000 kilometers per second. So we wanted to detect those diffuse H1 emission with MeerKAT. So Marx introduced this new subphases where you would have been classified this as phase one group, except that only one members are detected. So these are potentially new members that is acquired by the group. So in 2021, they applied for MeerKAT time to observe 6 Hickson compact groups, 3 belonging to the phase 2 and 3 belonging to the phase 3, where we expected to find diffuse H1 emission. And I will be talking about this result. So the numbers here indicates the percentage of predicted H1 mass detected in the center and also detected in the whole VLA field of view. So if you see more than 100%, that means that the groups are H1 rich. So if it's below, then it means that they are highly deficient. Okay, I was told to give some numbers for you to think about the strength of MeerKAT. So thanks to Betsey for introducing column density sensitivity limit, because that is the numbers that we are we radio astronomers are talking about. So this is a mongoose survey that Betsey already talked about, a survey of 30 nearby galaxies. So these are targeted survey of individual galaxies. So and VLA observations of nearby galaxies. So for Mongoose, the distance is less than 25 megaparsec, and for the things data with the VLA, the distance is less than 15 megaparsec. So you can clearly see here the column density level that you can reach with Mongoose. So this is 55 hours observations with MeerKAT. Okay, so you can reach a column density level below 10 to the 18. Of course, this depends on your imaging setup, like Betsey told before. You can smooth it to lower resolution, but you lose the linear resolution. Okay, but you increase in sensitivity. So this is the SKA1 mid 10-hour observations, 100 hours, 1,000 hour observations. So just to give you a visual eye. This is a sensitivity limit at 10 to the 21, where you only see the gas in the belonging to the disk of the galaxies. And as you go lower in column density, you start to see extraplanar gas. So you can, and if you go down to 10 to the 17, you can really start to see the connection between the disk of the galaxy and the cosmic web. So this is why people want to go as low as possible. So these are some of the H1 key science projects defined in 2014, but be aware that, like Lourdes said yesterday, this might likely change depending on the result that we have with the MeerKAT precursor telescope, or with the SKA precursor telescope. So you can get the result H1 kinematics and morphology of 10 to the 10 of galaxies out to redshift of 0.8. So this is already a very huge achievement for H1 people. High spatial resolution studies of interstellar medium in nearby galaxies, multi-resolution mapping studies of the interstellar medium, H1 absorptions, and the interface with the intergalactic medium. So this is a comparison of the sensitivity limit that we achieved for our H1 observations of Hickson compact groups with MeerKAT compared with other surveys like Mongoose here. Okay. And this is our sensitivity limit. Typically at 60 arcseconds, we achieve a sensitivity limit of 6.6 10 to the 18 atoms per square meter. So in total, our observing time per group is 6.25 hours. So the noise level is roughly 0.3 millisensky. We tried different tapering, so we are still discuss the correct imaging setup for our data. How much time?
You have 3 minutes.
Okay.
Plus extra 5 minutes.
Okay. So this is well, I want just to show here the noise characteristics of our data. So it looks random. There is no no artifacts. So this is the noise as a function of channels. So like I said before, the medium noise level is about 0.3 millisensky. So the data reduction was done with the SPSRC. With 24 CPUs and 108 plan to reduce the data. So I'm comparing here the MeerKAT spectrum, our MeerKAT spectrum of HCG16 with previous GBT observations. That there is very good agreement. So these are only the spectrum taken within the GBT beam. Okay, so this also highlights that our calibrations went very well. So here already you can see the strength of MeerKAT. Okay, on the left you see previous VLA observations, and this is our MeerKAT where we detect very huge H1 emission, especially in phase 2 groups. Okay, so this is previous VLA observations for HCG16, phase 2 Hickson compact groups, which I want to
And this is our MeerKAT, so you can already see the improvement. So for example, they didn't see these tails that we discover here in our MeerKAT observation. So we detect a lot more H1 for phase 2 groups. So this is another illustrations where we detect these tails is much more pronounced in MeerKAT. Okay, very nice three-dimensional visualization of these groups created by SKA, where you can change the thresholds here. So you can clearly see the tails connecting the individual group members. When you see this in 3D, okay, so another thing that we noticed is that we also detected member galaxies at a large distance from the center, but they are mostly late type spiral. Well, they are mostly gas-rich galaxies, late type. So again, another nice phase 2 groups. So these are composed by 9 members, most of them tidal dwarf galaxy members. So these are strongly interacting merging galaxies, this ANC complex. So we also detected, so this is previous VLA. Compare it with our new H1, you can see that we also detected a lot more H1 in this galaxy. A nice, again, a nice three-dimensional visualization of the groups. Okay. So you can rotate and see all the features. So this is very impressive result. Again, we detected some members at very large distance. Most of them late type galaxies. So this is HCG91. So probably less impressive than the previous phase 2 groups. Probably because this is a other phase 2 groups. So for phase 3 groups, we were a bit disappointed. So this is previous VLA observations when they didn't detect anything. Okay, but we detected some galaxies in the centers, high surface brightness H1, but no diffuse H1 component. And again, optical images of the members. In HCG90 also, we didn't detect any, so this is the only gas that was, only galaxy that were previously detected by the VLA. And we detected something in these galaxies that is nicely aligned with this optical and we wanted to make sure that this is real detection. So this is a position velocity diagram of these slices here. So in HCG97 also, we didn't detect, so this is phase 3 groups. We didn't detect any diffuse H1 emissions, but we detected a high surface brightness emission and a lot of emission, a lot of galaxies at very large distance. So you can see this is 1 megaparsec. So we asked these questions, okay? What is the area that, well, if the H1 were distributed uniformly at a certain column density level,
what is the area that needs to be filled in order to achieve the missing H1 mass. And we would need to fill this very large area to retrieve this missing H1 at this column density level. But how do you spread this the H1 emission to this very large area when the rest of the galaxies are not disturbed? So this is an open question, and how can the H1 survive? So this table just summarized that for phase 2 groups, we detect a very extended H1 emission, but in phase 3 groups, we are still missing about 10 to the 10 solar mass. Thank you for your attention.
Okay, if there is no question.
There is one online question. Ask?
Hello, can I ask?
Yeah, sure.
Okay, oh, very interesting talk. I think it's just a curiosity on the 30, the 31 group, the HC 31. So this is all the observations are amazing. So have you seen the merger hypothesis? Had you confirmed that for the high gas sulfur planet galaxy?
Well, we are still not in that stage. So we have just finished reducing the data and still trying to release it to the community. So that is things that we need to address using advanced kinematic analysis at a later stage. So we cannot really say anything about that at this stage.
Okay, and about the missing H1 in the phase 3, so do you think it's the molecular gas content should be the culprit, or is not that?
The molecular, well, in some groups, some of them have, well, in the advanced states, for example, some of them have very faint or no detected CO emissions, and some of them they have some CO emission. So, well, like if I remember correctly, in HCG 30, for example, which is one of the very advanced groups, there was no CO emission there, so no molecular gas. So hopefully the molecular gas has, yeah.
Thank you.
And it's not because of metallicity, because if you look at the optical properties of these groups, yeah, they have high metallicity. So the CO, local CO detection is attributed to the interaction in the groups.
Okay, thank you.
Okay, I think we can have one more question from Juan.
There was Stefano, I'll do it. Raise hand. I think Stefano was first, but.
Okay. Oh, can you unmute Stefano?
No, sorry, I was just selecting the window and I didn't check that I raised my hand, but it was unwanted.
Should I?
Go ahead. Sure.
Yes, I wanted to come to Pepe that for Hickson 31, I don't think we are going to learn more about the merger because the main gain of MeerKAT in these groups is the sensitivity to faint or extended features. Because something that is important to, I think, to know is how in what sense MeerKAT is better than the VLA, and it provides so the distribution of the antennas in MeerKAT it fills very well the central part, the UV plane, so it's very sensitive to what a single dish would see, but with the resolution of an interferometer, and also it gives a very large field of view. You can have up to 1 degree field of view And with the VLA, the field of view at 21 centimeters is like 19 or 20 arc minutes. So if we do a lot of work with the tidal features, which are more and more enhanced with MeerKAT observation in Hickson 31, as you have seen in the movie, we may infer something, but I don't think it's going to be that we are going to resolve much better the central part of the merger, because this is a tiny region in Hickson 31. And concerning the missing H1, something I think would be very interesting, and some people started doing it, but I don't think there are follow-ups, is to do deep H alpha observations. That would be very interesting, because we don't see so much X-rays, so I don't think it's so maybe it's ionized gas and we can see something in H alpha. So still these groups are a mystery.
Thank you, Lourdes. This is very interesting. Yeah, there are some intergalactic H2 region has been discovered also in Hickson. I mean, in the Stefan Quintet, for instance, where no H1 was present. So you see extended region with very, very, very faint, but emitting in H alpha.
And Hickson 16 also.
Okay, so let's thanks again, Roger, for the nice talk. Javier Zaragoza will be talking about the detection of tidal dwarf galaxies.
So I'm just going to talk about a project that I started before joining SKA. I joined SKA 2 months ago. So this talk is not going to be about because it's something I started before, but it's related with JPass and also with H1 gas. And in fact, with this work, it started while I was in Mexico, and also Jairo Andrade Alzate, I guess he's online today. He's also, while he was also in Mexico, we were both there. He helped me in this work, so he's also involved. So here I have a summary of things that we can study. What? Maybe. I press something? Okay. Well, here I know it's a summary about some things that we can do with JPass survey or also with H1. So on the top, these are things that we can do with JPass, like to study galaxy evolution, like observing galaxies at different redshifts, fossil records using the stellar population synthesis, or studying specific moments of the evolution of galaxies, such as galaxy interactions. We are studying these steps of galaxy evolution is important because galaxies suffer a major transformation when they interact. And these three things are things that we can do with JPass survey. And here on the bottom, I put things that we can do with studying or observing H1. Some of the things. Of course, there are more things. Here is a picture or a cartoon that also Rosa showed yesterday about the baryon cycle in galaxies. And well, the important thing about H1 is that it traces the external parts, as we have seen in so many talks. In the circumgalactic medium, so in the external parts, not in the disks. Also, there are disks of H1, but not in the stellar disks. I would say it's in noise. It is mainly in the external or in the halo of galaxies. And well, this I guess is important. Also, Rubén mentioned today. This is also important for JPass because I guess most of the IFU projects, Khalifa, Manga, or observations with Muse focus on the central parts of galaxies and forget about the external parts, and of course with JPass we can know we have the external parts of galaxies. And well, this is you cannot see here anything, but this is a famous MeerKAT-Smith relation, which of course it contains the H1 in this axis, and the H1 role in galaxies. Well, it's not always important. For example, in the main stellar disks, the gas there is mainly molecular gas, but again in the external parts, the H1 is the main component, and also in dwarf galaxies, and I guess that Ricardo is going to talk about dwarf galaxies more than me. And then one of the fundamental relations, the baryonic Tully-Fisher relation, relates the baryonic mass with the dynamics of the galaxies. It's also, well, it's a fundamental relation, and there is debate about if that dwarf galaxies are in the obey the baryonic Tully-Fisher relation, and it's because some of them have dark matter, some of them don't, and because it's very difficult to measure the properties of the small and faint galaxies. What I'm going to talk is about galaxy interactions today, or specifically about tidal dwarf galaxies. So in this picture about galaxy evolution, that is also for me is very helpful. So what I'm going to focus is in studying the fast or the evolution when it's fast, and also it depends on the environment. So I'm going to focus about this. I have been involved in this project with Beverly Smith since 2015, I guess. She led the observations of a lot of interacting galaxy pairs with Galax and also with Spitzer. So at the end, what we have in this spiral bridges and tail sample is 46 interacting galaxies observed from the ultraviolet to the mid-infrared, and also the Sloan and so it's very interesting sample, because you have larger field of view compared, for example, to IFU studies. So this sample is still, a very good sample to study galaxy or interacting galaxies, where the field of view is very important. And we have been working with this sample, studying star formation and tidal tails, and how these galaxies evolved. But what I'm going to talk today is about the most recent work I have been doing related to this sample, and is looking for detached tidal dwarf galaxies. The motivation to look for this one. These objects are forming in galaxy interactions. They are made of gas and young stars in tidal features or outside of tidal features. So they lack, or the lambda cold dark matter predict that they lack dark matter. So it's important to, well, if you observe these galaxies and you confirm that they don't have dark matter, so everything is in agreement, which is good, or not. I don't, depends on your taste. But what is also important is that the survival of these tidal dwarf galaxies, Synergies, is uncertain. So we don't know how many dwarf galaxies today are or come from tidally or from interacting galaxies. So they have a tidal nature, because we don't have enough statistical studies. So sometimes what we do is, what people do is to look, for example, for the oldest ones. That is the survival time scale, so have some estimations. One way we thought this would be a good idea is to look in this sample for the detached tidal dwarf galaxies. So, and detached, well, before going there, and also one thing is that the existence of these galaxies has implications in the finding what we call dark galaxies, which are dark matter halos that failed to convert the gas into star, because you can find one H1 galaxy, one dark galaxy that just have H1. And you can think that this is a dark galaxy that didn't form stars, but no, it can be also a tidal dwarf galaxy that you don't see you don't detect the faint stars. So why is important to study the touch galaxy? So this is one of the most classical tidal dwarf galaxies is this one here and this one here, and they have been studied a lot, but they are still connected through a tidal tail. So they are still well, it's connected. And so one way to look for the oldest one is to look for the ones that are not connected. They are detached, of course, with a definition of 25 magnitudes per arc second square. And also it's important because they are more isolated, so they can be easier to study. And so we look for candidates in this sample using especially the mid-infrared, but also the ultraviolet. And we selected 25 candidates, but in this sample. But of course, you don't know if they are galaxies or background galaxies. And here I show you two examples. This is one candidate, and this is another one. No, so what we did is to observe spectra. We went to observe in fact, the best 15 candidates with long slit spectra in the 2.1 meter telescope that Mexico has in San Pedro Martir Observatory. So we observed the spectrum to check if the redshift, specifically if the redshift coincides, but then we study more things. And here I put you the ones that we confirmed spectroscopically, so the 6 tidal dwarf galaxies that we confirmed that at least they have the same redshift. So it's this well, at the end there were 6, although this one I think, or we think, is a dwarf galaxy, but the rest they are tidal dwarf galaxy because it's in the tidal name. So we confirmed 6 of them spectroscopically. We see clearly the emission lines. Of course, we are biased towards the objects that have gas and star formation, because they are the other ones are almost impossible to. Well, at least I still don't have I'm not sure how to confirm the ones that they are not forming star. But if you observe the emission lines, you are so these are spectroscopy. They are with the redshift. They belong to the system, and these then 5 of them we confirmed that they weren't part of the systems, and the others didn't have emission lines. Well, so we know that they are, for example, they can be a pre-existing dwarf galaxy. So we can use the fundamental galaxy relations, specifically the stellar metallicity versus stellar mass, or also the nebular abundance versus the stellar mass. So these are if the galaxies are pre-existing dwarfs, they should be in the relation with the other dwarf galaxies. But if they are tidal nature, they probably are tidal dwarf galaxies. So we fit because they have observation from the ultraviolet, as I said before, from the ultraviolet to the mid-infrared. We can fit with Sigal, with well, the details are here, but at the end we touch galaxy candidates, and well, of course, what is good about Sigal is that it's Bayesian, so it gives it has a very good estimation of the uncertainty, and unfortunately, the uncertainty in the stellar abundant in the stellar metallicity is very large. But what we can say is that they are 75A and this one seems or to be from tidal nature. So tidal dwarf galaxies, real tidal dwarf galaxies, and the other not. But then we can also use the nebular oxygen abundance with the lines we observe. We could use the S calibrator from Rubén and Grebel. And then with this nebular oxygen abundance, we already five of these candidates are tidal dwarf galaxies, while the one that the largest, so the most massive one, is probably a existing dwarf galaxy. There are also other observations of these systems, but focused, and this is the thing. The observations were focused on the main disks of the galaxies, and they didn't cover this here and this here. They are long slit or multi-object, so they didn't go to the candidates. And this one is Muse, and Muse was just covering one of the disks of this system. So they don't cover, or typically the other observations don't cover the places where the tidal dwarf galaxies are. So you need, or to go specifically with your instrument, or use, for example, a survey like JPass that goes deep enough. This is how you would see these things. These are not real data. So yeah, I just went and put how we would observe these tidal dwarf galaxies in JPass. Also, if I did it well, I took into account the noise. And so in principle, the brighter ones, we are going to see them in oxygen, in H beta, and also in H alpha, and the faintest or ones. Well, maybe some of them depends. No, they are very close to the noise. Although well, I see H alpha, but I guess we should also the oxygen 3. At least we would be able to confirm the brightest ones and probably check for the best candidate. Okay. And the good thing about these tidal dwarf galaxies is that they had observations, all of them, the five confirmed the tidal dwarf galaxies. They had observations with the giant meter wave radio telescope in India. They had observation. They had an archive. Also, Chandrajit and Gupta helped us a lot with the data, and we were working with this data to start a study about the dynamics of these systems. And in fact, one student in Inoue, in Mexico, is analyzing the dynamics of these tidal dwarf galaxies. I show you here two of them, which is the two belonging to the R72 system, and we can extract the rotation, and we see rotation, we fit the rotation and extract the rotation curve. We are working on taking into account also the velocity dispersion, and to obtain the rotation velocity, the maximum velocity, which is the one which is using for example, the baryonic Tully-Fisher relation to check also if they are dominated or if they have dark matter or they don't. And here I show you interesting results, and this is where the synergy between JPass and SKA or precursors begin. And this is very interesting results from this year using the Western synthesis radio telescope, which has been explained or showed before this morning. And here and I didn't put the name, I forgot, but well, here the H1 is these contours, but the one interesting thing is that also this image is very large. It has a very large field of view, and the name of the camera for the optical camera is 1 degree camera. I think it's big. So, but at the end it's a 1 degree camera. So we have a larger camera, so we can do it we can do, I guess that faster in principle. And also we have the narrowband filters, no? That is also unique. So we can make this kind of combination and to study, you know, at the end the dynamics of tidal of galaxies. No, because at the end also the ultra diffuse galaxies are of course interesting, but probably with JPass we are not going to go deep enough to have this kind of objects. I don't know. And also what I think is interesting is how is the evolution in these objects. It makes at the end, for example, the MeerKAT Smith, the stellar populations and so on. So it's different, it's similar in these objects. And I leave here my summary, and I hope we can discuss a lot about this.
1 minute for questions. Any questions from?
MeerKAT. If I may. So we have no constraints on the amount of dark matter on these objects?
What?
We have no constraints, we have no idea how much dark matter, or where these objects have dark matter or don't have matter, or...
What object? The ones I presented?
These ones.
These ones, yes. This one, for example, this one from this work, yes, they do the estimations, and some of them they have dark matter, and some of them don't. This is also the interesting thing.
And the ones having dark matter, do they have like similar mass to dice ratio as similar galaxies? Which are not each one of that size?
Yeah, I think yes, but they have a very good plot. Sorry I didn't put it because I didn't have space. They have a good plot just comparing what you are asking, and I can show you later.
Thank you. I have one question. So do you think the depth of JPass is enough for the tidal, to trace the tidal features of this galaxy?
In principle, yes, but in principle, what I mean in principle, if what is the number? For example, what is I look for the number, but then I have if I forget. So one important thing is this number, no? So what is the depth in the I band in this unit? It's close to this number. I mean, it's 24.5 or.
Yeah, I think Mohammed could trace 25. Mohammed?
Okay. So 25. So
I think so.
So yes.
And for the JPass, I have a question. I am also interested in the low surface bracket. We are busy. So my main question is for the Renato. So do we have any plan for the deep observation with JPass? Because the main advantage of JPass is the large field of view, and to trace the very extended diffuse emission in galaxies, so we need deep observation. For example, I am interested on the outer disk star formation, but JPass may not be enough to trace the extended region of these galaxies. So do you think we have any plan for the deep observation of JPass?
Yeah, there has been discussions about making the discussion was about the NAP field, because we have a science working group that has been traumatized. They're transient people for the lack of cadence that we have. So we have been discussing about the possibility of getting one of these fields having a deep. So far, the discussion has been.
So it will be based on the survey basis or the proposal basis? If we request.
It is proposal based.
Proposal based.
Using 20% down.
Okay.
And I guess that we should, the talk today of Rubén García-Benito, he has already proposed these observations on a smaller area. So yes, maybe we should push to that project to go deeper.
Yeah, because when I was working on Lyman Alpha Nebula, I was having this problem. I couldn't trace the extended region of Lyman Alpha Nebula around the high redshift QSO. So I was thinking if we have an option for the deep observation, it will be very nice to trace the extended region.
Yeah, it will not be a small region. JPass is extremely inefficient to be a small region. So it will be a larger region in that particular. Few hundred. 10 square meters away.
That's the reason why they think that Rubén proposal is is
small,
yes. Well, he says small, but it's larger.
And since it's gonna be, everything going okay, it's gonna be a proposed, it's great to have more people joining the proposal. Because I think we have a very good, very strong case for that.
Last speaker of this section, Ricardo Amorín. He will be talking about the Hickson properties of dwarf galaxy with extreme emission line emerging from JPass. You have 30 minutes to take the questions.
Okay, good morning, everyone. For those who don't know me, I'm Ricardo. I just joined the SKA a few months ago. So just to warn you, I'm not an expert on JPass and JPass surveys. And I'm not also so this talk, some ideas that I was working on in the last few months on how to put together dwarf galaxy research on these possible synergies between JPass and SKA and their precursors. So this is quite an unstructured presentation. So I will start with my summary and with my outline at the same time. So just highlighting how dwarf galaxies are key in okay, so how dwarf galaxies are key in extragalactic research, especially because of their relevance as a building blocks, possible building blocks of more massive galaxies in the cosmic scenery, and also as laboratories for studying bias and properties, star formation, feedback at low metallicity, which also make us to learn about the more pristine galaxies at the early universe. So I will try to bring the idea of doing a sort of census of dwarf galaxies in the local universe with JPass, showing what I was doing with SDSS many years ago, and trying to highlight some different cases for different dwarf types, from the low surface brightness objects to the high surface brightness objects, and those which are forming stars in massive bursts. And also bringing some ideas for extremely metal poor galaxies, and also to characterize the environment of these galaxies, especially in the field, that may provide useful constraints to theory. In particular, I will talk about, in the last part of the talk, about dwarf galaxy groups, which could be also laboratories to study the triggering of starbursts and also quenching. So how do galaxies grow? So, well, we know from simulation, from theory, and also from observations that galaxies evolve through what we call the main sequence of star formation and gas consumption, gas accretion, and also feedback made possible this evolution in which galaxies at low masses goes up and down in this sequence, experiencing from time to time a series of starburst episodes where they grow in a very short time scales, and then after which, when they are massive enough, some other mechanisms make this galaxy to quench, to cease the star formation, and go to a more redder and passive part of the evolution. So in this sense, the recent simulation have shown that the distribution and the amount of stars and the structure of stars and gas in these galaxies, especially at low masses, where we can start to simulate the shape of the dwarf galaxies, can vary a lot depending on how these processes evolve. And have shown that the fraction of starburst in dwarf galaxies increases towards lower masses and in redshift toward higher redshifts, and the timescales, the number of bursts and the periods in which these galaxies have more quiescent phases also changes. So in this sense, dwarf galaxy mergers and also internal mechanisms like gravitational instabilities are very relevant. And it seems that it could be, has been proposed that two different mechanisms can act depending on the structure of these dwarf galaxies, galaxies which are more sensitive to interactions, where these bursts are originated with interactions or mergers, or these other cases where you have gravitational instability, a sort of breathing mode of forming stars. So from the observational point of view, we have different to classify and to census at some point the dwarf galaxy population in the local universe. This is one that we did some time ago with Sanchez Janssen, collaborator, using the DR7 from SDSS. So basically galaxies between 20 and 60 megaparsecs. It's a volume-limited sample where we find so mostly filled galaxies in the blue cloud and also in the red and transitioning phases. So we classify the galaxies between compact early types and diffuse late types, and all these galaxies have different properties from those more rare with low gas content, high metallicity, all star populations, to the ones that are experiencing strong star formation, compact ones, or more diffuse ones, mostly at low metallicity. So we also see point of view. And also it's important to highlight the differences in the gas fractions of these objects. So basically, what we see is that basically low mass galaxies are very efficient in converting values into stars. Basically, we see that the gas fractions of dwarf galaxies increases towards lower star masses, as these different works highlight here. So basically, most of these late type star forming dwarfs are very, very gas rich, as we have seen also in the talks here. And with the H1 gas distribution and kinematics, we can learn a lot about these different types of dwarfs. You can see mostly they are rotating dwarfs, but also from the distribution, those dwarfs, those with, merging or tidal dwarfs, or galaxies more in the transition to early type phases. Also, there are differences in the gas surface densities of these objects from the point of view of H1 and also from molecular gas. We see that, for instance, low surface brightness star-forming galaxies, star-forming dwarf galaxies, have more shallow surface brightness profile compared to the more star-bursting dwarfs like the blue compact dwarfs. Also, the sizes of the extension of these H1 halos change, and also in scaling relations like this mechanical law, we can see differences not only in the molecular gas, which have low metallicity, is also difficult to trace. So basically, the star form, the BCDs and the most bursty galaxies are above, and the more low surface brightness dwarfs are below. So this is a good, I think, a good case for SKA, as Betsey has shown before, but also for JPass and JPass to explore, especially because of these regimes, we find very extremely metal pool galaxies that sits in these scaling relations in the bottom part, deviating from the normal trend, the trend of normal galaxies in these relations. We have done some work years before with the single dish observations. These are from Effelsberg, 100-meter telescope. The H1 contents of this population of extreme metal galaxies that have metallicities below 1/10 solar, and that resemble the young pristine galaxies at high ratio. So one important aspect of these galaxies are that they show inverted metallicity gradients. So basically, the low metallicity of these objects are coincident with the regions where they have the more intense star formation, and this has been interpreted as a signature of infalling gas, which fuels the star formation and dilutes metallicities in these regions. But there are also other mechanisms that can produce these kind of things. Also, accreting modes comes from interactions or from gas which is recycling onto the. Several questions in dwarf galaxy research that I highlight here that I think that could be useful to think about projects for synergies between especially JPass and SKA or precursors in the short term, basically related with the mechanisms that governs the dwarf galaxy growth, basically exploring the star formation efficiency and the triggering of starbursts in these galaxies, and the spatial and temporal propagation of this star formation that can be mapped at least in the local universe, and try to quantify the fraction of starbursting and quiescent dwarfs in that respect. But also important, and I think I will highlight here, is the effects of feedback on the ISM, which are related with the chemical enrichment, the photonscape of these galaxies, which are not tomorrow, but I will focus on the environmental effects, which I think for JPass, which is a very wide survey, can be also interesting. So basically investigating interactions and merging in these galaxies. So in that respect, with the census that we did with the SDSS, we could find that mostly more quiescent dwarfs are always located in the vicinity of a brighter or more massive companion, whereas the star-forming dwarfs, the bluest galaxies, have the closer companion, the closer bright companion, very far away. So this is represented here in this 2D histogram, according to the different spectral classes, and also you can see this in these two high histograms. So this suggests necessary condition to cease or to quench star formation in these sort of galaxies. Therefore, I mean, suggests that the internal mechanisms like gas removal or exhaustion are not sufficient to quench these galaxies. Of course, this is something for debate. And also, I mean, in that respect, we need to think that many of these, in particular, extreme emission line galaxies or starbursting dwarfs, comes in pairs or in groups. And this is an ideal laboratory to explore dwarf galaxy interactions in the absence of these massive companions. Many of them are also found in low density environments like voids or close to voids. And the current paradigm, mergers of smaller galaxies should occur at low masses, as we see also at higher masses. So groups of dwarf galaxies should be present or need to be found. So basically, that was something that we have done. Also, other groups, like for instance, in this work by Stewart and collaborators, that found very rare groups of dwarf galaxies only, so without any massive companion. Also, recent illustrative simulations show that these are extremely rare, but they are very interesting and useful because, as I said, basically these kind of dwarf galaxy groups should be more frequent as soon as we move to higher ratios. So these are our own examples of these dwarf galaxy groups, and in particular I highlight these ones because these are small groups that consist of starburst plus post-starburst dwarf galaxies, which are also very interesting because tell us something about the temporal progression of these interactions and bursts and ignition and cease of star formation. In the very few cases that we found in SDSS, this sort of groups, we find it usually associated with tidal features, so suggesting interactions. But also, as these groups are extremely rare, and also starburst plus post-starburst in the same group, and also in low-density regions are also rare. This suggests us that these interactions or this temporal progression of star formation occurs in very short time scales. So H1 data could be essential to characterize the dynamical characterization of these objects, and also for the interpretation of the star formation histories of these systems. Well, this is to highlight the members, as you can see. So different types of starbursting and non-starbursting galaxies in the groups. These are other pictures of these objects. Some of them with these extended tails, including many young star clusters here as well. And well, one of the questions that we made some time ago is what is the H1 content of these objects? So we took a couple of them and observed with the GMRT in India, and in particular in this system, which this galaxy is an extremely metal-poor dwarf starburst, very well-known galaxy, and this one is a post-starburst. So you can see the SDSS spectra of this central region, which is the brighter region, without any emission line, but a very blue continuum, typical of this post-starburst galaxy. And the other one is basically same kind of continuum, but plenty of very high equivalent with emission lines for this object. And this is the H1 distribution. You can see that this galaxy is a very round and kinematically it's a disky galaxy. The post-starburst with a hole in the center, suggesting that there is no H1 gas. This has been recently confirmed with BLA observation, tracing the more shallow H1 content, and suggesting that some processes remove the gas here, or remove or exhaust or consume the gas. There are two options: feedback, of course, due to the previous star formation in this galaxy, because we have erode and heat and consume the gas, the neutral gas in this part of the galaxy, but also interactions can also make this kind of behavior. As you can see, there is a long tail here, which seems to be due to an interaction. There's plenty of young massive clusters which have similar age to the ones that we can find in the main body of the galaxy. But this tail has no H1 at all. So we are also conducting some analysis of the ISM of the individual galaxies, in particular for the starbursting one. We have MUSE data and also HST data to study metallicities, all the ISM properties, the warm gas phase, and found that very nice metallicity dependencies with the star formation rate densities and things like that, that we also want to use to compare with the coal gas content. So basically, this is my summary and the ideas that perhaps we can discuss in the discussion session. Basically, I mean, JPath can provide an unprecedented census of nearby low mass galaxies, I think, that will provide accurate ratios to characterize environment of these systems, quantify the number of galaxy pairs and groups in the field, identify the star-bursting galaxies from low surface brightness or more quiescent or post-starburst galaxies. This can be done thanks to the normal filters, as I show here. This is a nice example of one of these extremely short galaxies. Also, we can learn about ISM result properties and star formation histories from these data sets, identify tidal features like tails or run pressure features in these objects. At the same time, SKA, the precursors, current precursors, can provide radio counterparts for these objects to characterize the interstellar medium and to trace the large-scale environmental effects that this can suffer, these galaxies, especially from the H1 spectral line. We can trace mass, distribution of coal gas, estimate gas fractions, and analyze the dynamics of these complex systems. And radio continuum is also interesting to study feedback effects on the ISM, and also to interpret the star formation history, basically the effects of feedback from supernovae, cosmic rays, or magnetic field. This can be done with the LCD feeding the larger wavelengths from the radio continuum. So this is also happy to receive questions. Thank you.
Very quick question. It's a short question.
So how many of these dwarf pairs have you found?
Well, pairs a lot.
There's interacting dwarf.
Yeah, pairs a lot, but the interacting ones, very few. Very few. This is a volume limited survey, the volume limited sample between 20 and 60 megaparsecs. So this aims to be nearly complete between 2.5 magnitudes. So the bright end of the dwarf galaxy population is this volume. So basically, these objects are extremely bright. Less than
They would be tiny to observe with H1, right? Then result. If you were
result, especially result, you mean?
I mean, like for rotation curve analysis that you mentioned there, for example, if we were to observe them with H1, wouldn't they be too far away? That you don't have enough resolution element to study, to make a rotation curve analysis, for example.
Well, for this object, we haven't tried, but this object is 30-40 arc minutes. 30-40 arc seconds diameter in the optical. So I think with interferometry, with this data comes from GRMRT. I don't remember exactly the spatial resolution, but I think it's I'm not an expert.
Yeah, GMRT, it's hard to say. It's one that really depends on the weighting.
Mhm.
But if
Yeah.
it's 40 arc seconds in size and optical, like VLAC array is 15 arc seconds. So you can easily
15.
put a few beams across
Yeah.
it with the current H1 facility, and then MeerKAT, you know, you can do better. So
Okay.
I'd say it's feasible.
Okay, let's thanks again, Ricardo. We have time for the discussion.
Oh.
I thank you for the speaker for the session. Just an announcement. So because of some thinking about moving the discussion session for this afternoon. So right now we have to go for lunch, and after that we have to visit the observatory before the sunset. So we're gonna be back here at 5:30 p.m. And so we're thinking that at 5:30 we can have the discussion session. That's the idea. Everyone is okay?
I don't know.
Yeah, at 5:30.
Yeah, because we have some gap between after the observatory visit and the dinner will be here in Galactica anyway.
So the plan was that at 5:30 we're gonna be.
We were gonna have to talk to each other anyway, so we might as well.
Exactly, we are going to.
It's gonna be a more organized.
Somebody's leaving, then we'll repeat the discussion tomorrow. So people online will
Yes.
will be online.
Yes, so people online.
We'll meet. I don't know if they will be listening on the other side. But
So we're gonna, like, the Zoom connection is gonna be available for
Yeah.
people online at 5. I'm really sorry that I know that it's not ideal for everyone.
When he's asking for the time, so 5:30.
5:30.
Yeah.
Yeah, because we have to leave the observatory at 5 the latest, so at
Yes.
5:30 we should be here.
So we should be. I'm really sorry about that. But that's it. Thank you.
Or there is my email sign during discussion.
Yeah, I'll send it.
Shall we start? Yeah? Okay. Okay, there are 7 people online. So, continuing a bit with the discussion that we had yesterday, I think that there are like 2 main lines that we can discuss. Synergies with the planned surveys that exist already, or the possibility of applying for open time in future proposals, things like that. So on the first side, I think that one of the things that I wanted to raise is, Renato is outside. Do you remember which is the area that it's overlapping between Rosita and JPass? Do you have that number in mind?
No de área. Rosita and J pass.
And JPass, yes.
I don't remember the figure of Renato. I think he said something like a few thousand, 2,000 maybe.
He's outside.
Was planned
I can go.
1,000, but I'm pretty sure it's a few hundred.
Only a few hundred. I think it was about 100 in a player one. I think this morning he said 1,000.
Because that field is relatively low, right?
Yes.
So that will be, I think, one of the obvious cases for synergies. So the SKA pathfinders that are covering that region, everything that is below 30 degrees or 20 degrees, are an obvious overlap, because in that area there would be X-rays, J-pass, and also radio.
Right.
So science cases for an area in that region would be an obvious line. Renato, we have a question for you.
I know. I have an answer for you. So keep in mind that this was done by eye. Okay. And so the numbers may be a little rough. This, I was estimating the coordinates here. So like I mentioned before, so this would be, this is the Eurozone. That's the tier 1. Tier 2 would have, in principle, less priority, it would take more time to get observed in principle. So this is, well, this is actually the 40 degree. If you look at, can I use it on?
Turn it on.
So this one is the
Renato, could you use the mouse to point, because it's difficult to see it from online.
So this is the desirable by us, to limit, but not necessarily by the SKA. That's like the worst possible case. This is like 40 degrees declination. So this is for the SKA 1 mid possible, which was all the way here, from here to here. We would have more or less 900 square degrees in the high priority and a lot in both of them. And so, but they prefer the 40 is supposed to be better to do a 20. I guess we have representative here that agrees with that. So if we do the desirable, this number reduced to 180 in tier 1 and near 2000 in tier 2. So here is the second case where I try to put as much as Ali did the drawing as close as possible to some number here, which is to be 20 degrees, and this would be SKA1 low. So going out to H20, we have about 200 square degrees in tier 1 and 1800 in tier 1 and 2. And the desirable would be 10 degrees according to that, and that would reduce significantly. We have 0 in tier 1 and only 900 square degrees in tier 2, which are those around here. So, yeah.
In which area is it, Rosita?
It's below. The German one's the downside.
So that the downside of the black line, right?
Yes.
So the black line separates the east from the west in galactic coordinates.
So that part of the sky is the one where we have the most overlap between different wavelength ranges, and that should be covered by SKA precursors. Well, apart from LOFAR, RACs cover that part. EMU will cover also everything below 30, I guess.
RACs goes all the way to 49 degrees.
Yeah, but then with very innovative beams. But EMU should cover also in the, if I understand well, I don't
You're
know.
talking about this area here?
Yeah. Yeah, because that area we will have X-rays from Rosita radio, and then from the J-pass side, tier 2 is going to take longer. Would it be possible to move the seats?
The seats
south.
Okay, let's.
What's the
seats not, but
hold people, don't let them fight physically.
I don't want to start a fight, but let's say, would it be possible to have high priority tier 2 tires?
So I just talked to Ali about this because we actually have, I showed you here. This is weave.
This is a challenge. I have my answer.
Actually, it's this blue here, and we are not getting this area full because
Come on.
Everything's converting to this particular region, and what Ali said, he will not kill anybody on site if we expanded that region by calling tier 2. I would be, no, of course, this area is very nice because it also has the EFEDs, the Rosita full observation, there, which is a gamma here. As Cosmos, the underscreen camera. Last, there's a lot of, if we had to go in efficient somewhere, I would think that would be an interesting place.
So, Renato, if you can go back to this one. Okay. No, the 3 deck minus 20, but really doesn't matter. All right. Just to give you an idea of how the use of the seeds. So, and how the tiers were defined. So, science groups to send me feedback on priority science and priority pointings, right? So try to grow where pointings would maximize scientific feedback, right? So, or scientific return. So there were some areas of the sky where this was significantly obvious. There was actually one area of the sky which is very nearby this. Oh, right, sorry, thanks.
I can point where you're pointing.
Right, thanks. This area around 45 degrees declination and 12 hours, that was an area which was where most things were converging. So there's one seed which is obvious, is the only place in the sky where we already have calibrated the 56 filters, 57, which is mini JPass, which is the one nearby. So that sky area was needed, right? So you start thinking from there. And then there was another important thing. We had to stay away from the Milky Way. More on this tomorrow. I will mention for out of completeness that the ecliptic is not our friend. I think I mentioned it yesterday because of the presence of the moon. So for a few days a month, actually more than a few days a month, this can be quite problematic, especially in summer when it becomes really problematic. End up in December last year when there were a series of 4 pointings which were somehow extreme and sort of framed our situation for us. It was a series of pointings which were so obvious and so beautiful that people said, well, this is an obvious open time proposal, so we can forget them. They frame our observations, and we go for them. So one of them was JNEP, which is declination 67 and red ascension around 16, so where Renato is pointing. Another one was Virgo cluster. Actually, to be honest, the whole discussion, because the footprint had been discussed for years. The whole discussion of the footprint was born because of 2 things. One, there were a series of dents where JPCAM is not efficient. And then there was another thing, which was something that I took very personally. It is a pity that we didn't have Virgo. So I was like, let's try to push. Turns out Virgo didn't manage to enter in this one either, because it's just below here, right? So I swear, I tried my best. The thing is, again, who would go against a proposal to observe Virgo with 56 narrowband filters? I mean, it's such a beautiful proposal that goes straight forward. And then there was the Kepler field. Oh, right. And then there was M31. Again, M31, again. So over lunch, Renato and I were chatting about the idea of extending tier 2 towards the south, or even creating a tier 3. The beauty, now the thing is, how do the seeds eventually work? You can think about it as a series of priorities in pointings. So we have one pointing, which is literally one pointing, which has a given priority, the seed, right? Once you observe it, this gets out of the pool of observations. But the pointings around, they are raised their priority at seed level. So let me use this one as a very good example. Right. Thanks. So this one is a very good example because it's actually, and also this one, because it's comparatively close to between the border between tier 1 and 2, right? So at some point, in principle, you always observe among the pointings with seed priority, you observe the one with the minimum air mass. I'm not sure if radio astronomers use air mass, but that is the highest elevation over the horizon. Now, the fun part is normally this means that you grow from the pointing towards up left. Actually, not even up left, towards around 40 declination, right? Because it's where we are located. So, but nothing forbids us to do what we are actually doing with this pointing, with this very first pointing, which is the weird QSO, where we're actually going towards the south against all logic. Because we have this MOU with weave, and we have to deliver pointing. So here we're growing towards the south because we cannot grow towards the north to give them fields, to give them targets. So all of this to say, here we started observing, and we are in a region where we are in the Hirosita region, right? So we're
like if you grow towards north or towards.
So that's exactly where I'm going. From here, we could, in principle, start moving towards the south.
Okay.
Again, is it ideal? No, it isn't. But actually, the nice part of this is that you're actually sitting on top of the meridian, right? So you can actually grow in both directions. Actually, from there, you're naturally moving away from there. So what I'm trying to say is, yes, from here we can move in either direction. If we decide that if we want to go towards the south, we can do it. And probably we have to, because unfortunately we have with all the given respect and all the friendship with the German part of Hirosita, but this is suboptimal for us. But we can move towards here. Now, creating another seed here is against fights any logic because of what Hector was explaining yesterday. To repeat it today. We need to grow. JPass has a very big inertia. So you need to start pushing a lot. You need a lot of time, but then it's not growing by itself. So from here, now if we start growing towards the south, we start to grow significantly. All of a sudden, right, you saw the figure, right? It literally goes up quite fast. So can we do it? Yes. What happens at the border? What happens at the border is the priorities go up one level. So if one is tier 1 priority, goes to tier seed priority. lowest thermal, we just hijack it and we observe it. If it's a tier 2, becomes tier 1, right? So we're going to have this border effect. Can we extend tier 1? That is already that becomes a little bit uncomfortable. Sure, we can do it. Can we extend tier 2? Well, tier 2 is already scraping the Milky Way. This is plus or minus 10, the plane of the Milky Way. Mind you that I stopped plotting it because it was confusing people. I was plotting the interstellar extinction due to the Milky Way, but people started to get confused, so I stopped doing it. So plus or minus 10 is a very good indication of where the Milky Way is. But there are regions where you can push a little bit more, and regions, and I'm referring to this specific one, around between 4 and 6 hours of the right ascension, where really you cannot get any closer to the Milky Way. I would love to get any closer to the Milky Way, but for a survey like JPass, you can't. So can we grow more towards the south? Yes. Growing more towards the south, you start having the risk that you start hitting at these regions around the corners, where in regions where you have very high extinction. Now, those regions perhaps will never be observed. The thing is, the moment you start making corners with JPCam stops being efficient and you start throwing away lots of data. So this is something you don't want to do. To some extent, this ended up being the best exercise of having an efficient survey with good scientific return for most of it. One wants to do a survey around the equator. That is a 20% down.
The effects are about 9, about here. Yeah.
So that means that for tier 1, what we have in common between Rosita, radio surveys, and us is order of hundreds of degrees, maybe 200, maybe 300, but something around that number.
Yeah.
So that region, if I understand well, this is a question for the radio people, is going to be well covered in continuum by LOFAR and also possibly also by EMU. Is that correct? Because
yeah, I have to check EMU. So I guess the thing to know about the ASCAP surveys, of which EMU is one, is that relatively recently, within the last year or so, they basically did an exercise to reallocate time based on sort of the performance of the facility as it is now. And so that, for example, is why Wallaby is now not quite all sky. I don't know what EMU's approach was, if they said we'll go a little bit less sensitive, but still do all sky, or if they gave up on sky.
I saw the paper about the pilot field, and they show a coverage that it's from plus 30 to.
I mean, that pilot
what
paper is 2 or 3 years old. I mean, I would really check their website, to see what's happened in the last 6 months, basically.
But the thing that would be missing there is a deep H1, which precursors are going to cover H1 in that area. Wallaby is going to cover everything below 40 or 30 as well.
Earlier, so they're going to do, they're going to do up to the equator, basically skipping the southern cap. And then they're going to do a little strip above. I'm not sure exactly what it is based on the images I saw. You could contact them to see. And that's also like where the E Rosita is. There might be some aperitif, but not much, because that's actually a little low for us in declination. Fast will cover there.
Fast will cover there.
Fast will cover there. So that's similar to alfalfa in terms of its unresolved, but it will be about twice as sensitive. And so in terms, there will be total H1 content information.
Okay, so I think that the message more or less is, if I would have to think in the best synergy between the different facilities, I would think in projects that cover a few hundreds of degrees, in that area. And the only thing missing in probably is, well, no, if fast, we would have also the H1, so.
Yeah, and there's alfalfa there right now, so.
And other possibilities that people applying for open time. And JPCAM is not efficient if you need the 54 filters. But if you're applying for open time and you don't need the 54 filters, the situation is different. For example, we have trays with the broadband filters. So let's say if you need broadband filters in a more equatorial area, that is not inefficient for us to do, if I understand well.
I mean, as long as you want to cover big chunks of the sky, it's still efficient. I presume that in open time, we'll be asking for surveys as well.
Yeah, but imagine that southern radio astronomer is interested in covering one of the 20 or 60 degree precursor patches with a limited number of filters.
No, that wouldn't work. But it would make sense. I'm thinking in the ABOS context, right? And if there is a bunch of small scale radio surveys covering that area just below the black solid line, it would make sense to submit a proposal covering those 2,000 or 1,000 square meters. In that case, I understand that JPass wouldn't be as efficient as going further north because of the nation, but still would do a good job.
So I reformulate my question. What would be your advice to a southern radio astronomer that wants to observe something that is close to the equator?
I would ask him to coordinate and to participate in a wider proposal that motivates the observation with full filters of that southern chunk that, tier 2A, which would be good for us. Actually, this would save us very soon. Well, actually,
but that means that they will need to go to larger areas.
Right. Yeah. I would understand that that's where JPCAM is more efficient. Right?
But yeah, increasing the amount of scientific return is always a plus in the proposal. For example, if the one that I mentioned today, you're looking for clusters, halos, if you get, let's say, 200 square degrees, you may have something like 1,000, 2,000 clusters there, and maybe 5,000 to 7,000 groups. That'll be something that can serve many groups, actually, including perhaps cosmology as well.
Right, including cosmology. And that would feedback on the JPass strategy as well, in the sense that if this happens, and then we have external groups providing this data, which actually overlaps with the JPass area, the data has to become public after how long? A year?
Yeah, but I think that it's going to be unlikely that the committee is going to approve a project to observe what is going to observe JPass. Yeah. So I mean the goal is that to observe something that is not in the JPass footprint, that's something that has some probability to be approved. But to observe something that is going to be observed by JPass in 1 year or two.
Well, that's the thing. It's tier 2, right? Depending on, I don't know how critical time is in this game. Can we wait for 3 years? Can we wait for 4 years? I don't know. It depends on the speed, right?
If I were to do something like this, perhaps one thing that I would do is similar to the idea of proposing for M31 or Virgo. I would propose to observe, I was checking the size. I would propose to observe the E-fence area. The E-fence area is already Irosita full depth. So you're not going to get better X-ray data for the next 40 years.
Mm-hmm.
And then I don't know about the radio surveys that are already available there, but it's something which is.
But how big is that patch?
Sorry, 140 square degrees.
140.
That's in the limit.
This is really the limit.
I don't know if there's much equatorial LOFAR data.
We do have LOFAR data. I'm talking as the opposite now, but from LOFAR, the equatorial fields are challenging, but we do have points there and quite a lot.
What's the problem with the ecliptic? That the moon comes a lot and you said it can become really slow. So
Son, I have to give up some, right? I'm giving up. And I'm advising, this is not something that I would do.
So another comment I wanted to, regarding the potential use of a few filters, we also have to be very careful because the JPass filters, as Tony explained, they are located in each filter tray, also because of technical reasons. So we cannot think that we are changing filters from one day to the other to JPass, and tomorrow we do this synergy project, whatever, for SKA. So I think that is something to be considered very carefully. If there is a real need to observe a few filters, then maybe we should go for one filter tray with 14 filters, and we should build
what happens
for the future, in years, not now. Okay? So it's
if in the open time proposal there comes a group that says that they want to map with H alpha certain region of the sky, and they have the funding to build the filters. So they put the filters on the tray.
That's something that can be, that's something that will be offered when we open the call for new legacy surveys. That's a possibility. Actually, you know that for the legacy surveys for the JST, one of the projects is building their own filters. Okay, but it's more simple for TAT camp.
Yeah.
Okay,
I'm just speculating about the possibilities that they have.
This will be a possibility. But take into account that if you only want to observe with 3 filters, for instance, like one for the intensity of the line and for the continuum in both sides, it's going to be very inefficient too, because the filter is going to be only affecting to one CCD. So,
or you could build, for example, two H alphas, and you put the so it's the blue ones in the center and the red ones in the extremes.
Yeah, but that will have to. My recommendation at first sight, I mean, of course, it has to be done with a lot of detail, is that if something which is different to JPass wants to be observed, this will require its own filters and its own filter tray, so that you insert that and then you change your mind and you do a different survey strategy, a different survey, everything is different. Okay, and that will be optimized for the purpose of this project, because everything we are discussing now, the observing strategy, the footprint, the camera, the filter tray, everything is optimized for JPass. Thing we want to is not going to be optimal by definition.
Javi, a question for you. So, how do you think? Of course, the committee is a committee, and it will take its decisions at the end. It will have some recommendations and guidelines before they meet. So, if there is a bunch of older surveys in the radio and the X-ray, which would be interested in having JPass-like data, in order for this to go through open time committee, then we need several requirements. One, it should not be in the JPass footprint. Right?
I think that's a disadvantage, because it's going to be done yes or yes. So
in this context, I think what seems obvious is that then what we should, I guess it makes sense that people who are interested in JPass-like data team up in that proposal big area that is outside the footprint, and it can be observed minimally,
exactly.
a minimum requirement, minimum efficiency, which means not going too far south. But if you go back to the slide 20.
Carlos, I think that's correct, but I think before that, I think we should agree in what was the scientific goal.
Right.
Because maybe with 200 square degrees, we are done. Or maybe we need 2,000, but for that, we need to
well, it depends on
discuss.
Yeah, but it's not only radio. The thing is that here we have the radio community, but we have somebody interested in the X-ray community as well, right?
Yeah.
So, maybe it makes sense to put together, people from different expertise and say, okay, we have this multi-wavelength coverage in this big chunk of area, which still can be, which is outside the footprint of JPass, but it still can be observed. Like for instance, they stripe from 0 to 20 or something, right? Not sure how far south is this. Alessandro will tell us how difficult it is, right? From 20 what? From 20, what is it? 18, from 18 to 8, right? around from 0 to 15 around. Could that be observed? Would that be, I understand this radio data there, right? There will be a lot of X-ray data. Maybe it makes sense, a big proposal to cover that in open time. That's right, right?
Yeah. So
That is something that I would do.
I had 3 questions now. Let me start asking before I start forgetting. So I was not part of the of J+ open time selection process, and I was wondering if it's an open time and you apply, it's a competition between the applications from the outside, independent of the usage by JPass, right? It's like a guest observer program. I'm sure, of course, if you do something that people can use later, it's always good, it's always a plus, but that's not necessarily a condition. But the second question I had about this is, you could still apply for the open time in a JPass footprint with a different exposure. The JPass will not do, right? So that's also open time.
It's like a deep field.
Right. I need this much more. So JPass will be there, but not enough. So those are my 2 questions. And my third and final, I understood from Ali is that it's not that you cannot get here, right? The thing is they grow. So if yes. Wow.
The mouse has 2 fingers.
Can be growth.
No, not that mouse. The mouse.
Okay, so as you go down, let's say here, you're growing continuously this way, and that way, right? So that's what I understood. So at some point, if you're going here, then you start having all these issues with going close to the way, past the ecliptic somewhere here, and so on. So it's not, can you grow like that?
Yes.
So you're still increasing in area, but you are kind of away from the forbidden zone. So those are questions that
The forbidden zone actually would be the ecliptic, which I didn't plot on this. Right?
Yeah.
It passes the equator around 12.
It passes, I don't remember. But on the other plot it was. So yeah.
I had this somewhere here.
At some point I felt it was too many.
Maybe it's another figure that I don't have.
Nothing.
The really crowded one.
Oh wait, it's this one.
That had the HSC.
Right here.
No.
Right here. So it's crossing. That's 8.
Yes, it passes the equator to the right extension 12.
Yes. So the gamma field is actually. So maybe I don't know if you can grow in a diagonal way, you can optimize it. How complicated it is to choose a path that you can still grow, and optimize it so that you get just most of the area.
You can actually get 2 patches which are similarly distant from the ecliptic plane so that the ecliptic bothers you equally. Certainly not on the ecliptic, because otherwise you're going to be always annoyed. But if you have 2 patches, when the moon is close to one, you can observe the other one, and vice versa. Just thinking out loud, I should see that.
And I don't understand exactly.
You may, again, I'm thinking in terms of having 1 patch, which could be even slightly elongated, but then having 2 seeds, 1 on each side of the ecliptic, then you start growing on either side of the ecliptic. Because growing on top of the ecliptic is going to be more complicated, right? But you want to grow on different sides of the ecliptic. Just thinking out loud. But that is another sky which I think is.
On the left, you have the Virgo.
Pardon?
On
Yes,
the left of the
left.
ecliptic, you have the Virgo.
You're being dragged.
some point you have to observe through that.
Yeah. Just in case that.
I don't know with JPCam how far away you have to be from the TV. I don't know. And I think so far we are still using the conservative.
We're still studying this because there seems to be some reflection. We don't know where it's reflecting. When pointing away from them, we still get vision. So we need to make a study like, okay, what's the exact angle of the moon when this happens? Because it's not always close to the moon that we have. So it may even be the dome. Maybe they are actually dome reflecting light. So we still don't know the full way of the moon affecting us. We still need to study that. Yeah.
I don't mean to cut off the discussion, but the feeling that I'm getting is that there is a lot of technicalities that you have to take into account, right? And also, not to jump from one topic to another, but I think one of the reasons of these or goals of this discussion is that we also identify areas where JPass and H1 data can be of certain synergies, as the name of the meeting suggests. So if I don't know, from all the discussions and talks that we had yesterday and today, I wanted to direct a bit the discussion to whether we've seen some potential areas where we could focus a bit and try and find some science that is feasible, not only with the MeerKAT, I mean the SKA precursor, but also the pathfinders. Like Betsey mentioned this morning, there are a lot out there. There is alfalfa, aperitif, and you mentioned recently lofa and so on. So,
well, right now aperitif will be very nice because there is a lot of area in common. Yeah. So that means that try to put it together the product from aperitif, the H1 or the radio continuum, with all the kind of product that we can get from JPass, just in terms of galaxy, the stellar mass, star formation rate, also ionized gas, separation between star formation and nuclear activity. So there is a lot of also environment, selection of group and cluster. So there is a lot of things that could be putting together between the aperitif and JPass.
So which one is the one that ILOTS is running on? ILOTS? Yeah.
That's low, like what international LOFAR. And ILOTS doesn't really exist yet, right?
No,
Like
it doesn't
that's.
exist yet.
No, it was. So end of 2025 was the beginning.
Well, Shane is.
Then it took like 5-6 years. So
Yeah, it has to be allocated. They're reviewing proposals right now. But yeah, I mean, I think it's quite likely that it will happen. But it's not approved project. But yeah, I mean, I think this is a good point about, because we can think, right now we're talking about a lot of technicalities, but we could also think, what is it that we can do in the next couple of years with existing data sets or data, data we're already planning, so that then in the future we can either say, okay, let's push to something more equatorial because we've shown that there will be cool science there, or let's push for like MeerKAT or SKA time that's a bit further north, because again, we've shown there's cool science there. But if we think sort of what's at hand and what can we do now to sort of motivate pushing facilities a little bit outside their natural comfort limits because the return is worth it.
So in that case, with the current seeds, the most likely ones of overlap would be those here. They're close to 20 degrees and are going to be growing to both directions.
Actually, the one on the right is already growing southwards.
Right.
Because of
yes.
Yeah, but so like, for example, if I look at sort of what you have currently, I go, okay, what I call the fall sky, I think you would call the fall sky too, the 22 hours to 4 hours or whatever, that declination, that has alfalfa H1 right now, you know, and there's public catalog, you can just go. It's only global gas content, but that's the first thing. And then I look at your other seeds and I go, okay, the spring sky, that's more northern. I'd have to get out and put them on the same scale, but there's probably some aperitif data there. That data is not sort of as immediately to hand and easy to work with as the alfalfa data. It's not at that final stage yet, but it's there, it exists. We can make things on demand and stuff, you know. But, you know, sort of really think what's easy, what can we do now? There's lots of radio continuum surveys. You can see, yeah, what coverage there is with existing lots. VLA is doing a 3 gigahertz survey, VLASS, VLAS. There's always the Godot Classic NVSS, still great, you know. So
this is my question to the optical people. From the science we've seen this morning and also yesterday, right? Did you come to identify some areas where you think if you have H1 data, you can improve or continue for that matter?
Yes, in the low surface brightness and extended emission, there's a lot of things that we can do. But well, the main problem is that with JPass, we want a huge area. I mean, it gets efficient when we go in large areas, and the area is much larger than 1 or 2 galaxies, even nearby.
Yeah.
So what the most important thing is just have overlap or increasing overlap area. That's I think that's the main problem from our side, from JPass's side. Because there's always going to be a lot of galaxies in, you know, in 100 degrees squared. So that a particular galaxy is not going to be the problem, but or a particular science. For that case, you can do all redshifts, but the overlap with existing radio data, so we can, yeah, as was mentioned, we can then, find the future science cases, show papers that they can show this. Write papers they can show this. Because like, you know, statistically, we can stack the H1, H alpha, for example, emission, and then correlate that with stacked H1 emission, I don't know, find something, or like with AGNs and how they behave, the different lines.
Okay, for example, tomorrow I'm going to talk about the AGNs, but one of the obvious synergies is to correlate the properties of the jet with those of the stellar population in the host galaxies. So that can be done with J plus and LOFA, for example. So you can focus on the massive galaxies with extended radio emission and then measure the kinetic power of the jet and trying to characterize the duty cycle of the jet from the radio information and connect that with the stellar population properties of the hosts.
I don't know if you can hear me.
Yes. Yeah, we do.
Yeah, I am as Juan. I am also working on some. Too loud? What?
Not disconnected. We didn't hear you.
Oh, now it's fine?
Yes. So.
Okay, yeah, so I was saying that as Juan, I am also preparing some cross matches between my galaxies selected from J Plus and different currently available radio surveys. So I will also present some of these tomorrow. I am currently doing it, so I cannot promise a lot, but something will show up.
For example, in the case of Alejandro, correct me if I'm wrong, but he would be interested in covering large areas deep in H1. Is that right?
Yes. I was listening, and yeah, I am still trying to figure out exactly, given some of the constraints, for example, about redshift 0.1 to 0.2 from the radio observations are going to play into the area that we need. Because if we have to focus on sources at below redshift 0.1, then even with JPass, we will have to stick to, we will have fewer sources. We need thus larger areas. So yeah, I would need for extreme objects, for very rare objects, which I guess it's beyond my domain. It's also an interest for the whole for other JPass projects. Do you need a large area? I was hearing 200 square degrees, and I think something can come out from that from my side. I guess 1,000 would be nicer, but I mean, I guess we are far from pinning down exactly the numbers.
Let's focus on quality, not quantity.
Yeah, but quantity allows you to select samples with higher quality.
And the camera is designed like this. Of course, at high quality is also
very good. To get to that.
It was from cosmological survey, so.
Yeah.
And it is still there.
Forget that.
We can support Galaxy evolution.
I mean, from an external, I'm not very close to each one, but I mean, for what I see is that there are already fields where you have overlap. And there's a bunch of science cases that you guys are developing, they're presenting, and it makes total sense that you guys get deeper into these different science cases. But for the current discussion right now, if I understand correctly, we want to see how we want to grow in the future. So if those science cases are actually validated and confirmed, what we should think about is how to grow, right? And where to grow, right? And in this sense, from what I understand from Ale, we have structural constraints, right? It seems to me, and I want to insist on that, but I understand that there are many radio surveys that are southern, right? And they could just try to get a bit higher, right? And we can try, so to me, it looks like the natural way of overlapping is the region that we mentioned before with the caveat that Ale was saying is that the ecliptic, and we understand this, the ecliptic goes from 0 hours and it crosses at 12 hours, right?
Crosses.
No, however, it has to, at some point, either from 0 to 12 or from 12 to 24, it has to go up towards through the tier 1 or tier 2.
Yes.
Right?
Up to almost 23 degrees. And then it goes back down and crosses back at 0. And then it goes down to minus 23. Then it goes back up to 20.
Like it goes up to plus 23 at what hour?
Right.
At 16 hours?
Yeah, just about.
Here.
Yeah, 6 and goes to 20.
Okay. Okay, so that chunk is kind of, so it makes more sense to actually grow on the other side, right? So then,
the high RAs.
Higher RAs, right.
Above 12.
Right.
But it's not just that it makes more sense, it's that it will happen. Because there won't be observations where the moon is.
Right.
They're going to be slower.
Yeah, so it will naturally go faster on the other direction than towards the eclipse.
Yeah, but I think that still we need to, all this must be driven by science. I mean that the way to grow JPass is well defined. Okay, now I agree also with Betsey that now we have data, we have JPass data, tons of JPass data. We are starting to have some JPass data, and there is already quite a few data from precursors and so on. So I think it's time to get together to start thinking in what we can do, and from that there will appear science cases that maybe will tell us, okay, so it is worth that we modify the way to grow because this is a hot topic. Okay, but now, I mean, to me, I don't have enough information to say, well, now we have to change, we have to go to the south, or we have to give a higher priority because I think we still need to understand what for. Okay, the good point is that, well, we have that yes or yes will have some significant area in common with SKA, and this is going to grow with time. Okay, both JPass and both SKA that doesn't exist yet. So we have still many years to come up with new ideas, with new strategies. I mean, this picture that we are showing, it took 10 years okay, of discussion in the collaboration. So we can imagine that once we enter the radio, let's say, side, there will be also some discussion. So if it's worth it, I'm sure it will be worth to do some modification of this, but it needs to be very well justified. And to come up to that, we need to start working. And I think it's very interesting, all the science cases that have been presented, H1. So, but how many galaxies we need, or what is the minimum area, what is the depth? So it's something that we still need to understand.
And like technically, just you know, from one like in the extended emission part, where I see we have a lot in common, but like one problem I have is that I really have no experience with radio data. So like I'd really like to find someone here from the radio people who are interested, and then we can start maybe collaborating and seeing finding the coverage areas and then yeah, getting some statistics, because in our team we're working on extended H alpha emission and all the on the emission lines of the galaxies to find the one with extended emission, and then if we can cross match those or even get the H alpha map, H1 maps of those same galaxies. Then we can start some papers and we can see some. And so something I think like this, at least from my point of view, is the lead of one of the is this we need someone to help us from the radio side. We have none of us have any background in radio. I guess the only person who understands radio data in SKA is Juan.
Well, that's why he's leading the discussion.
But he's too focused. Yeah, I mean he's already busy. So I really
that for example is a type of practicality that I would like to see come out of this, this discussion, because we may spend hours talking about technicalities, but at the end it's like I don't know if we may leave this place with empty-handed and not having anything to build on basically.
One thing that I propose it, and I think it would be very helpful, is to do the match of the existing catalogs with our catalogs.
Sure.
Yeah. And it will start science cases just because you have already the match between the sources. So this is something that we should do. I propose this, and I think that would be a easy first step to get things going.
Would you agree?
Okay, so then.
So are we gonna stop and do that right now?
But probably this is the basic thing, so to cross-match the catalog to see which is the information. But I think that we have to talk also, or we have to think also about the not only the integrated property of H1 or radio information in general, also about the galaxy. We have also to think about extended where we can put it together the property of the galaxy, the spatial resource property of the galaxy, and the H1. For example, kinematic information. We don't have kinematic information for the galaxy, which is so that will be a very complementary analysis.
Why don't we just open a Google Doc and write down all these potential projects? And at least we come out with a list of ideas.
A paper that we were discussing yesterday is the one by Hardcastle. Hardcastle published a match between LOTS DR2 sources and optical counterparts in different surveys. So there are 4 million sources there, and so the match was not only of the integrated properties. They were doing a complex process to associate, for example, extended radio lobes with the optical source in the center. So that is already something close to, because once you have that association, you can go to the data and then check for the extended emission. For example, for that catalog, they have 58% of the sources have good photometric redshifts. But there are 85% with optical counterparts. We could provide photometric redshifts for more sources than there are in that catalog, probably.
That's another. Okay.
Again, the problem for this from my side is that I don't know the radio surveys, for example. If someone
Yeah, I mean, that was the point of this. I think like Javi shared some, I shared some, and I guess, you know, I say like, I don't necessarily have a lot of, I'm hesitant to volunteer myself to do science right now because I'm barely doing my own. But like, definitely for sure, if you come to me and say, this is the sort of data I'm looking for, I can help you start and where to find it, right? Like that is knowledge I just have ready to share. Wendy has it for things I don't have it, you know. You've got all the people at Granada who are, you know, you have H1 questions, there's a whole expert group there.
Yesterday, Javier gave a very good review of surveys, right?
Yeah.
And the talks, or at least his talk, is already available on the Google Drive. So I downloaded it already.
It's gonna be available on YouTube?
Yep. I will make the talks ready.
They're very traceable. And we can keep talking to each other.
Nah.
So you're the radio guy, so are you in the 205 megahertz? What are the?
I was working with that, quite, not so much radio, but more millimetric, but yeah. I'm the closest to radio frequency radio.
So I'm the only one with SKA work with relay or something like that?
Probably.
Another radio. I was gonna tell all of this on the science, a day for science. Yeah, I realize, like, people don't know what my experience is.
But I work with MBSS, if that counts, I don't know if that counts. Anyway, Mairu, are you writing, I mean, are you making public these minutes, the minutes of these kind of discussions?
So, yeah, to be honest, we are just taking notes for about what we're discussing, but what I can do is make a sort of summary for tomorrow also.
Okay.
Rubén raised the hand. Who? Rubén, do you want to talk?
Yeah, can I share the screen?
Yeah.
I take mine.
So this is just taking on what Rosa said about resolved populations. So this is can you see my screen?
Yep.
Okay. So this is all the extended sources in the optical, okay, on the equatorial plane. These are very extended sources, so more than 1 arc-minute. And at the end, that's why I propose this part. But the concentration of the most number of extended galaxies in this area. But the largest one is this square here. So this small one is the EFITS one. And as you see, the most concentration in the optical of extended sources is in this area. I mean, on the equatorial plane. So this is the first cross mass just with different optical catalogs. And if you want to have, at least from the extended optical sources, the most number of objects in your footprint, this is the area, more or less the area to go.
Yeah, but Rubens, that's what we were talking before. This footprint that you have, this kind of depth, it has shrink.
The J-pass footprint.
Yeah, that's what we were just talking. This is not anymore the footprint.
And by extended, into what surface brightness? I mean, what parameter do you use to define extended? Like based on effective radius or radius up to?
Yes, 826. 826.
Up to 20. Okay, that's good. Yeah, we can use a catalog like that and match with J plus that we already have a lot of data and see where.
So that's a system of every single survey radio by memory. Which one crosses mini JPass?
Where is mini JPass?
80s.
Can I have a right assumption and declination, please?
It is what?
With
55 in declination, right?
Yeah.
It's
And
45.
240 something in array.
Can I have that in hours? Divide by.
One of those.
About 14 hours.
Yeah.
It's the other one.
No,
Yeah.
it's the other,
That one?
that one.
So aperitif might cover that. I'd have to check. Could be well within our footprint. Our footprint is very odd for very reasons quite similar to this discussion in some ways. Lots would be there, NVSS. First probably. First should be there because it's
I think that Kelly was looking.
Yeah, I mean, so like,
apparently there is aperitif.
if Kelly said, then definitely there is. I mean, so Kelly, like, because you want H1 data, tell me, that's great. I just tell Kelly. So you can shortcut me.
Yeah, around 1445 aperitif is there.
Yeah, no, I mean, we're definitely in that right assumption range and that declination range. It's just, are we right there? But I think we should be. Yeah, so there should be some H1 data. There's a continuum data over the whole sky, just to varying levels, right? And so it really depends on the frequency you want and the resolution you want to do your science, if there's something that will suit you or not.
J plus, there is only 1 degree squared effectively, so we're not gonna have too many.
Yeah, I mean, honestly, in 1 square degree, the odds that you have in
Yeah.
a single H1 galaxy is pretty small. It's like 1 per 5 square degrees, or is it 5 per square degree? It's one or the other. It's something like that though. But the H1 sky is mostly empty, mostly just because we're very volume limited. We don't go, like there's lots of optical galaxies because you go out much further in redshift, so you have much more volume.
So probably J plus and S plus are better. Because over there we have 1,000.
Just to add, so maybe we can pull up the chat. I don't know if this is possible, but Shane is saying that the mini JPass is also covered by lots here too.
Yeah.
This is available as well.
Yeah.
Yeah, and so like in the continuum, there's gonna be lots of radio continuum sources. So, depending on what you want to do, what your science is, that can be great. And if there's also aperitif, if you have 2 very different frequencies, you then get spectral index, which tells you, is more interesting than a single, frequency, so.
Anything else? Any other idea? Or you want to visit the museum?
I have to leave at 7:30 or.
We found a new driver, which is Javier Zaragoza, who kindly offered himself to go with the band, maybe in 1 or 2 rounds.
But what time do we have to leave?
It's not far, so.
So we are supposed to be at 8.
At 8.
At 8 in the restaurant. So it's a 10-minute walk. So if you want to walk, we can go together. And if you want to go by the minivan, Javier can take you 1 or 2 seats.
So we have about 1 hour.
Yeah.
Okay.
Yeah, 1 hour.
Okay, so
we finished? We wrap up?
We finished. What time do he was in the schedule?
Let me see. It is 9:20. Seems like we'll be a few minutes. That's just taking the morning break at 11 and then discussion at 2. Yeah, tomorrow 9:20.
Okay, okay. So we close now. For people online, thank you for being here. We'll meet tomorrow at 9:20. Okay.